Hello there, and welcome to Science for Sleep, a place where curiosity slows down, explanations take their time, and science is allowed to unfold gently without asking anything urgent of you. Tonight, you're invited to settle into a question that almost everyone has seen written somewhere, perhaps on a classroom wall, a book cover, a t-shirt, or the side of a mug, yet very few people have ever truly sat with in a quiet way. That short line of symbols, E = mc², has been called the most famous equation in history. But fame does not always bring understanding, and recognition does not always bring comfort. So rather than rushing to define it or prove anything, we are simply going to stay with it for a while, let it breathe, and see what it is actually saying when no one is in a hurry. Before we go any further, take a moment to notice where you are listening from tonight. Perhaps you're already in bed, or maybe resting on a couch, or letting this play quietly in the background while the room grows dimmer. What time is it for you right now, in your particular corner of the world? It is interesting how questions about physics often feel distant and technical, yet they always arrive at a specific moment, in a specific place, with a specific person listening. That alone tells us something important. Whatever E = mc² means, it means something here, now, with you. If you find this slow exploration calming, or if the steady pace helps your thoughts loosen their grip a little, you're very welcome to like the video or subscribe to the channel. It helps this small pocket of calm reach others, who might need a quieter way into science as well. There is no pressure, just an open invitation, much like the one you accepted by pressing play. Now, when most people encounter E = mc², it feels a bit like being handed a locked box with no instructions. You're told it is important, you're told it changed the world, and you're told it explains something fundamental about the universe. Yet no one pauses long enough to explain what it actually means in plain terms, or why it matters beyond textbooks and headlines. Energy = mass times the speed of a light squared. That is usually where the explanation begins and ends, as if repeating the words slowly will somehow unlock their meaning. But words alone do not always help. What helps is context, patience, and a willingness to approach the idea from the side rather than head-on. At its heart, this equation is not about complicated math, nuclear reactions, or genius minds working at impossible speeds. It is about a relationship. A quiet, surprising relationship between things we once believed were completely separate. For a very long time, matter was matter. It was the solid stuff. Tables, stones, planets, bodies. Energy, on the other hand, was movement, heat, light, motion. One could push the other, transform the other, but they were not thought to be the same thing. They lived in different conceptual boxes. E = mc² quietly opens those boxes and shows that they were never really separate at all. To appreciate why this mattered so much, it helps to imagine the world before this idea existed. In everyday experience, mass feels stable. A chair stays a chair. A book does not suddenly turn into light. Energy, by contrast, feels fleeting. Heat fades, light moves on, sound dissipates. One feels permanent, the other temporary. Physics reflected this intuition for centuries. Mass was conserved. Energy was conserved. They were both important, but they were different kinds of quantities. What Einstein realized was not that one could sometimes affect the other, but that they were, in a deep sense, two ways of describing the same underlying thing. This is where the equation begins to soften into something more approachable. E = mc² is not saying that energy magically turns into mass all the time in your kitchen, or that your coffee mug is secretly glowing with destructive power. It is saying that mass is a form of energy that happens to be extremely concentrated. So concentrated, in fact, that under ordinary conditions it stays locked away, unnoticed, behaving like solid matter rather than flowing energy. The equation is a translation guide. It tells you how much energy is contained in a given amount of mass, even if that energy is not free to move around. The reason this idea feels so startling is because of that little squared term. The speed of light is already unimaginably fast. Squaring it makes the number enormous. This means that even a very small amount of mass corresponds to an enormous amount of energy. Not energy that you can tap into easily, but energy that is there in principle, woven into the fabric of matter itself. When you look at a pebble, you're not wrong to see something quiet and inert. But at a deeper level, physics now tells us that this pebble represents a vast reservoir of energy, bound up in a stable arrangement, not going anywhere unless the universe itself changes the rules. It is worth slowing down here, because this is often where explanations become abstract or dramatic. There is no need for that. You do not need to imagine explosions or cosmic events. Instead, think of it like this. Mass is energy that has settled into a very calm, very organized state. Energy is mass that is allowed to move, change, and spread. The equation simply gives us the exchange rate between those two descriptions. It is less like a spell and more like a conversion table, quietly telling us how deeply connected these aspects of reality really are. This idea did not emerge in isolation. It grew out of a deeper rethinking of space, time, and motion. Einstein was not trying to create a famous formula. He was trying to resolve inconsistencies in how light behaved. Light did not follow the rules that classical physics expected it to follow. No matter how fast you chased it, light always moved away at the same speed. That strange fact forced a reconsideration of what space and time even meant. As those ideas shifted, mass and energy shifted with them. The equation was not an add-on, it was a consequence. That context matters because it reminds us that E equals mc² is not a claim about power, weapons, or technology first and foremost. It is a claim about structure, about how the universe accounts for itself. It tells us that what we call matter is not a fundamental ingredient separate from energy, but one expression of it. This helps explain why stars shine for billions of years, why the sun can warm the earth without losing its shape overnight, and why the universe behaves consistently across scales that are otherwise hard to reconcile. Still, it is understandable if all of this feels distant. Most of us do not deal with energy in such terms. We deal with tiredness, warmth, hunger, motion. We flip switches and expect lights to turn on. We eat and expect to feel less empty. E equals mc² sits quietly beneath all of that, not intruding, not demanding attention. It is part of the accounting system that keeps reality balanced, even when we are unaware of it. For now, it is enough to recognize that E equals mc² is less a statement about extreme events and more a quiet sentence about unity. It says that the universe does not draw hard lines where we once thought it did, that solidity and motion, rest and change, substance and activity are deeply intertwined, and that insight, once noticed, tends to linger in the background of thought, reshaping how other questions are approached. So as you listen, allow your attention to drift without trying to pin everything down. Let the equation remain a presence rather than a problem. There is more to uncover, and it unfolds best when there is no rush to arrive anywhere in particular. It is hard to think of another scientific expression that has travelled so far beyond its original context as E equals mc². You see it in places where physics is not being discussed at all. It shows up in cartoons, advertisements, pop songs, and jokes. It is printed on notebooks, mugs, and clothing, often treated less like an equation and more like a cultural symbol. Most people recognise it instantly, even if they have never taken a physics class or solved a single equation involving it. That familiarity gives it a strange kind of presence. It feels important before it feels understood. Yet for all its recognition, very few people have a sense of what it actually represents in their lived experience. It is known in the way a famous face is known when you cannot quite remember why they are famous. You know you are supposed to nod, perhaps smile, perhaps feel impressed, but there is no real connection. the equation becomes a badge of intelligence rather than an idea that lives comfortably in the mind. That distance is not the fault of the listener. It is the result of how science is often presented, fast, compressed, and aimed at correctness rather than comprehension. When people first encounter E=mc² in school, it is often delivered abruptly. A teacher writes it on the board, explains that it connects energy and mass, mentions the speed of light, and then moves on. There is rarely time to ask what energy really means in this context, or why mass would be related to it at all. The equation becomes something to accept rather than something to explore. Over time, it hardens into a fact that sits on a shelf in the mind, labelled important, but unopened. Part of the difficulty lies in how compact the equation is. 3 symbols and a constant somehow claim to describe a deep truth about reality. Our intuition struggles with that. We're used to complexity being explained by long descriptions, not short ones. When something profound is expressed so simply, it feels suspicious, as if something must be missing. And in a way, something is missing, not from the equation itself, but from how it is introduced. The meaning is not in the symbols alone, it is in the story behind them, the assumptions they replace, and the questions they quietly answer. Another reason the equation feels distant is that the words we use to translate it are themselves slippery. Energy is a term that gets used casually. We talk about having energy, lacking energy, feeling energetic. In physics, energy is something much more precise, but that precision is rarely explained in a way that connects to everyday experience. Mass, too, is often confused with weight or size. So when someone hears that energy equals mass times the speed of a light squared, they are juggling vague ideas from daily language rather than clear physical concepts. The result is a sense of abstraction, even when the equation itself is deeply concrete. There is also the shadow cast by what the equation later became associated with. Nuclear weapons and nuclear power loom large in the public imagination. Even when those topics are not explicitly mentioned, they hover nearby. This can create a feeling that the equation is dangerous or overwhelming, something tied to forces best left to experts. That emotional weight makes it harder to approach the idea calmly. It turns curiosity into caution, and distance grows where familiarity could have taken root. But if we step back from all of that, from the fame, the fear, and the shorthand explanations, something quieter begins to emerge. E=mc² is not trying to impress anyone. It is not making a dramatic claim. It is stating a proportional relationship, one that happens to have enormous implications. At its simplest, it is saying that mass and energy are 2 ways of accounting for the same thing. That sentence alone, if allowed to settle, begins to change how the equation feels. To really feel this idea, it helps to let go of the symbols for a moment. Imagine you're looking at a familiar object, something small and ordinary, perhaps a book on a table. You think of it as matter, as mass. It occupies space. It resists being pushed. It stays where it is unless acted upon. Nothing about it suggests energy in the way a moving object or a flame does. And yet, according to this equation, that book represents a certain amount of energy. Not metaphorically, but literally. Energy that is not moving, not radiating, not available to warm a room, but present all the same. This is not an intuitive idea, and it does not become intuitive quickly. It asks you to accept that energy does not have to look energetic to exist. It can be stored, locked into structure, held in place by balance. Mass is energy that has found a stable arrangement. That stability is so convincing that we forget it is energy at all. We give it a different name and treat it as a separate category. The equation gently reminds us that this separation is a convenience, not a truth. Feeling this connection does not require imagining conversions or transformations. You do not need to picture matter exploding into light. Instead, you can think in terms of accounting. Physics keeps track of reality by counting conserved quantities. For a long time, mass was counted separately from energy. Einstein showed that this was double counting. There was only one underlying quantity being tracked in two different ways. E equals mc² is the conversion factor that corrects the ledger. Once you frame it this way, the equation begins to feel less like a spell and more like a clarification. It explains why certain processes release energy when mass changes slightly. It explains why the sun can shine steadily without visibly shrinking. It explains why the universe is not divided into rigid categories of stuff and action. These explanations do not arrive all at once. They accumulate quietly, like familiarity with a place visited many times. Another barrier to feeling the equation is scale. The speed of light is so large that it feels disconnected from everyday experience. We do not move at anything close to that speed. We do not see objects approach it. So squaring it feels like multiplying by something imaginary. This makes the equation feel irrelevant to normal life. But the speed of light is not included because it is exotic. It is included because it is a fundamental limit built into the structure of space and time. It is the same everywhere, always. That constancy makes it the right bridge between mass and energy. When you square that speed, you're not making the equation more dramatic. You're reflecting how tightly mass is bound to energy. The enormity of the number is not an exaggeration. It is a statement about how much energy is associated with even the smallest amount of mass. The reason we do not notice this energy is because it is balanced, contained, not leaking out. Feeling the equation involves appreciating that stillness can hide magnitude. There is a subtle emotional shift that can happen when this idea sinks in. Objects begin to feel less inert, not unstable or threatening, just deeper. A sense develops that the quiet solidity of the world is not empty of activity, but full of it, held in place by rules that are reliable enough to let us live our lives without thinking about them. The equation does not make the world feel less safe. If anything, it explains why it is so consistent. This sense of depth is often missing from popular explanations, because they focus on outcomes rather than meaning. They jump to applications, to technologies, to dramatic consequences. But feeling an idea usually requires staying with it before it does anything. It requires letting it sit alongside your existing understanding and noticing how it changes the way you categorize things. That kind of understanding cannot be rushed. So if E equals mc² has always felt like a slogan rather than a sentence, that is understandable. It has been treated like one for decades. But slogans are meant to be repeated, not inhabited. Sentences, on the other hand, can be lived with. They can be returned to, considered from different angles, and gradually integrated. This equation rewards that kind of attention. Knowing an equation and feeling it are not the same thing. Recognition can happen in an instant. Understanding takes time, and there is no disadvantage to moving slowly here. The equation is not going anywhere. Long before anyone wrote down E equals mc², long before energy and mass were spoken of in the same breath, the world made sense in a very particular way. It was a way that felt comfortable, intuitive, and closely aligned with everyday experience. Matter was the solid part of reality. It was what you could touch, lift, stack, break, or sit on. Energy, by contrast, was what made things happen. It caused motion, warmth, light, sound. One stayed put. The other moved. One occupied space. The other flowed through it. For centuries, this division was not questioned in any serious way, because it worked well enough to describe almost everything people encountered in their daily lives. If you imagine yourself living a few hundred years ago, this separation would feel completely natural. A stone had mass. A fire had energy. The stone could be heated by the fire, moved by a person, or shaped by a tool, but it never became fire. The fire could warm the stone or light a room, but it never turned into stone. They interacted, but they did not blur into one another. Physics, as it developed through observation and experiment, reflected this worldview. It did not see any reason to combine the two ideas. In classical physics, mass was a measure of how much matter an object contained and how strongly it resisted changes in motion. If you pushed a heavy object, it pushed back, not because it was stubborn, but because its mass gave it inertia. This resistance was predictable and measurable. You could calculate how much force was needed to accelerate an object of a given mass. Once set in motion, that mass would carry on unless acted upon again. Matter had presence and persistence. Energy, on the other hand, was understood as the capacity to do work. Work in the physical sense meant moving something against a force, lifting a weight, stretching a spring, heating water, or making a wheel turn all involved energy. Energy could change forms. It could move from motion to heat, from chemical reactions to light. But it was always treated as something that moved through matter rather than something that was matter. This distinction became formalized in the laws of conservation. Mass was conserved. If you started with a certain amount of matter, you ended with the same amount, even if it changed shape or state. You could melt ice into water or vaporize water into steam, but the mass stayed the same. Energy was conserved as well. It could change forms, but it could not be created or destroyed. These two conservation laws were seen as parallel but separate. They governed different aspects of reality. This separation felt reassuring because it matched what people could observe. When wood burned, it turned into ash and smoke. But careful measurements showed that the total mass remained constant if you accounted for everything. The heat and light released were energy, not matter. They escaped, but they did not reduce the mass in any obvious way. Matter transformed, energy flowed, and the books balanced. There was no need to connect the two more deeply. The success of this framework cannot be overstated. Classical mechanics, developed by Isaac Newton and others, described motion with extraordinary accuracy. Using mass, force, and energy as distinct concepts, scientists could predict the paths of planets, the behavior of projectiles, and the workings of machines. Engineers built bridges, mills, clocks, and engines based on these principles. The world behaved as expected. The division between mass and energy seemed not only sensible but essential. Heat, in particular, was once thought of as a substance. Early scientists proposed that heat consisted of an invisible fluid called caloric that flowed from hotter objects to colder ones. This idea fit neatly into the separation model. Heat was not matter, but it behaved like something that could be transferred. Although this theory was eventually replaced, it illustrates how strongly people felt that energy was something that moved through matter, rather than something inherent to it. Even when the caloric theory was abandoned, the separation remained. Heat was reinterpreted as the motion of particles. A hot object was one whose particles moved more vigorously. This explanation tied energy to motion, not to mass itself. The particles had mass. Their motion had energy. The distinction held. Chemical reactions followed the same pattern. When substances reacted, bonds were rearranged. Energy was released or absorbed, but the atoms themselves were conserved. The energy came from changes in configuration, not from the disappearance of matter. This reinforced the idea that mass was a stable backdrop against which energetic processes played out. Electricity and magnetism added new layers, but not new confusion. Electrical energy flowed through wires. Magnetic fields exerted forces. Light travelled through space. All of these were energetic phenomena, distinct from the material objects that generated or responded to them. Even when James Clerk Maxwell unified electricity, magnetism, and light into a single framework, mass remained separate. Fields carried energy. Matter responded to fields. The division persisted. At no point did this framework seem fragile. It was coherent, productive, and deeply intuitive. If anything, it felt complete. When problems arose, they were solved within the existing categories. New forces were added, new particles were discovered, but the underlying assumption stayed intact. Matter was matter. Energy was energy. It is important to appreciate how deeply ingrained this separation was, because it explains why E equals mc² was so unsettling. It did not refine an existing idea. It crossed a boundary that had not been questioned. It suggested that mass itself was a form of energy, not merely a container for it or a participant in its transformations. Before that suggestion, there was no reason to suspect such a connection. In everyday experience, mass does not behave like energy. It does not radiate. It does not dissipate. It does not flow. It stays put. It gives objects weight and solidity. Energy, by contrast, often feels fleeting. It moves, spreads, and fades. One feels permanent, the other feels transient. Physics reflected this intuition because physics is built on experience. It begins with what can be measured and generalized. For centuries, no experiment suggested that mass could turn into energy, or that energy could become mass. The instruments were not sensitive enough, and the processes that reveal this connection are subtle under normal conditions. The world did not contradict the separation, so the separation remained. There were hints, though, scattered and misunderstood at the time. Certain chemical reactions released enormous amounts of heat relative to the apparent changes in matter. Radioactive substances behaved strangely, emitting energy continuously without obvious fuel. But these were treated as anomalies within the existing framework, not as signs that the framework itself needed revision. Radioactivity in particular posed quiet questions. Certain elements seemed to release energy spontaneously, changing into other elements in the process. This was new, but it was interpreted as a rearrangement of matter at a deeper level, not as a conversion between mass and energy. The mass differences involved were too small to measure accurately at the time, so the idea that mass itself might be decreasing went unnoticed. In this pre-Einstein world, energy was something that happened to matter, not something that matter was. The two were linked but not identical. This made sense of machines, chemistry, and motion. It allowed engineers and scientists to compartmentalize problems. When you wanted to calculate how much fuel was needed to run an engine, you used energy. When you wanted to know how much material was required to build it, you used mass. The tools were separate and they worked. There is a comfort in such separations. They give the impression that reality is neatly organized, that different aspects can be studied independently without overlap. They allow for specialization and clarity, but they can also hide deeper connections. Sometimes, what appears to be a boundary is simply a habit of thought. The separation of mass and energy was not wrong in the sense that it produced false predictions. It was incomplete. It described a limited range of phenomena extremely well, but it could not account for everything. It was like a map that works perfectly for a city, but fails when you try to navigate the surrounding countryside. As physics advanced, cracks began to appear, not in everyday mechanics, but in the behavior of light and high speeds. Light refused to behave like a simple wave or a simple particle. Its speed appeared constant no matter how fast the observer moved. This alone did not directly implicate mass and energy, but it forced a reconsideration of space and time. And once space and time were reconsidered, mass and energy could not remain untouched. Still, before that shift, the world of physics felt stable. Energy was conserved, mass was conserved, the equations balanced. There was no urgency to unify them. The separation was not a mistake, it was a stage. Understanding this stage is essential, because it shows that E equals mc² did not emerge from confusion. It emerged from success. It arose not because classical physics failed everywhere, but because it worked so well that its limits became noticeable only at the edges. This is often how deep changes occur. They do not begin with chaos. They begin with precision that suddenly stops extending where it should. When light behaves oddly, when speeds approach limits, when small discrepancies refuse to disappear, the old categories still function, but they no longer feel sufficient. At this point in the story, energy and matter still occupy separate conceptual worlds. They interact constantly, but they do not overlap, Mass anchors objects, energy animates them. Energy. The universe feels divided into the solid and the active, the stable and the dynamic. This division feels natural because it aligns with how human senses work. We feel weight. We see motion. We feel heat. We do not feel the energy locked inside mass because under ordinary conditions it does not announce itself. This quietness is part of what allowed the separation to persist. If mass radiated energy constantly, or if objects lost measurable mass when they cooled, the connection would have been obvious. But the universe is conservative. It hides its deeper relationships beneath layers of stability. Only under extreme conditions do those relationships reveal themselves. It is enough to rest with the idea that for most of scientific history, the separation between energy and matter was not an oversight. It was a reasonable conclusion drawn from reliable experience. The fact that it eventually gave way does not diminish its usefulness. It highlights how much remains hidden even in a world that seems well understood. Long before the equation E equals mc² entered the conversation, something else had already begun to quietly unsettle physics. Something that did not look dramatic at first but refused to behave the way everything else did. That something was light. Not light as warmth on your skin or brightness in a room, but light as a physical phenomenon that could be measured, tested, and chased with equations. The deeper scientists looked at it, the more it resisted being neatly categorized, and the more it forced uncomfortable questions about speed, motion, and the structure of reality itself. In everyday life, speed feels relative in a very simple way. If you're standing still and a bicycle passes by, it is clearly moving faster than you are. If you're sitting in a moving train and another train passes in the opposite direction, it appears to move very fast relative to you, even though both trains may be moving at similar speeds relative to the ground. Add your own motion into the mix, and speeds add and subtract in ways that feel straightforward. Walk forward inside a bus, and your speed relative to the road increases. Walk backward, and it decreases. This logic works beautifully for throwing balls, driving cars, and watching clouds drift by. For centuries, physicists assumed light would behave the same way. If you move toward a beam of light, you should measure it moving faster relative to you. If you moved away from it, you should measure it moving more slowly. This expectation was not strange or careless. It was based on everything else that moved in the universe. Sound behaves this way. Water waves behave this way. Projectiles behave this way. There was no reason to expect light to be different. At first, scientists did not even think of light as something that travelled through empty space on its own. It was assumed to propagate through a medium, much like sound travels through air, or waves travel through water. This hypothetical medium was called the luminiferous ether. It was imagined as an invisible substance filling all of space, providing a background through which light waves could move. The idea fit comfortably with existing physics. If light travelled through the ether, then its speed would be relative to that medium, just as sound speed is relative to air. If this were true, then measuring the speed of light in different directions while the Earth moved through the ether should reveal slight differences. As the planet orbited the Sun, it should sometimes move with the ether wind and sometimes against it. Light travelling in the direction of Earth's motion should appear slightly slower or faster depending on the alignment. This was not speculation. It was testable, and physicists built careful experiments to test it. One of the most famous was conducted in the late 19th century by Albert Michelson and Edward Morley. Their experiment was designed with extraordinary precision for its time. They split a beam of light, sent the two parts along perpendicular paths, reflected them back, and recombined them. If light speed differed along those paths due to Earth's motion through the ether, the recombined light would show interference patterns that shifted as the apparatus was rotated. The result was unexpected and deeply unsettling. No matter how the apparatus was oriented, no difference in the speed of light could be detected. The light behaved as if the Earth were not moving through any medium at all, or more troublingly, as if light speed were the same in all directions regardless of motion. At first, scientists suspected experimental error. The setup was refined, repeated, and improved. The same result appeared again and again. Light speed did not change. It was constant, not approximately constant, exactly constant, within experimental limits. This constancy was not just puzzling. It was incompatible with classical physics. If speeds always added and subtracted, then a constant speed that ignored the motion of the observer made no sense. Something had to give. Either the experiments were misleading, or the assumptions about space, time, and motion were incomplete. Some physicists tried to preserve the ether by proposing increasingly complex explanations. Perhaps objects physically contracted in the direction of motion through the ether, masking the effect. Perhaps clocks slowed down in motion. These ideas were introduced as mathematical fixes rather than conceptual revolutions. They allowed the equations to work but did not explain why reality would behave that way. What had not yet happened was the realization that these fixes were pointing towards something deeper. The universe was not conspiring to hide motion through the ether. The ether itself was unnecessary. Light was not behaving strangely. The assumptions about space and time were: the speed of light, usually represented by the letter c, was measured to be about 300,000 kilometers per second. This number was already impressive, but its exact value mattered less than its behavior. No matter who measured it, no matter how fast they were moving, no matter the direction, the result was always the same. Light did not care about the observer's motion. This is where intuition begins to strain. Imagine chasing a beam of light in a very fast spaceship. Common sense suggests that if you move fast enough, you should eventually catch up, or at least measure the light moving more slowly relative to you. But experiments and theory insisted otherwise. No matter how fast you went, the light would still move away from you at the same speed. This was not because light was stubborn or magical. It was because speed itself did not behave the way people thought it did. The universe had a built-in limit, and light travelled at that limit. Nothing with mass could reach it. This limit was not imposed by technology or engineering constraints. It was woven into the structure of reality. Once this idea is accepted, even tentatively, consequences begin to cascade. If everyone measures the same speed of light, then space and time cannot be absolute. They must adjust themselves to preserve that constancy. Lengths must contract. Clocks must tick differently for different observers. Events that seem simultaneous to one person may not be simultaneous to another. These ideas sound abstract now, but at the time they were shocking. Space had always been thought of as a fixed stage. Time had always been thought of as a universal flow, ticking away identically everywhere. Light forced a reconsideration of both. Albert Einstein did not discover the constancy of the speed of light. That was already established experimentally. What he did was take it seriously. He treated it not as an inconvenience to be explained away, but as a fundamental feature of the universe. He asked what must be true about space and time if light always travels at the same speed for everyone. From that question, special relativity emerged. And from special relativity came a new understanding of energy, momentum, and eventually mass itself. The speed of light was no longer just a property of light. It was a conversion factor between space and time. It told you how much space could be traded for time and vice versa. This is where the story begins to bend back toward E equals mc². The appearance of c in that equation is not decorative. It is not there to make the numbers large or dramatic. It is there because c connects quantities that were once thought separate. Just as it links space and time, it links mass and energy. In classical physics, energy depended on mass and speed, but mass itself was independent. In the new framework, mass carried energy even when it was not moving. That energy was proportional to the mass and scaled by c². The speed of light acted as the bridge, y². Because energy involves speed squared in many familiar formulas such as kinetic energy. The appearance of c² maintains consistency across the theory. It reflects how deeply speed is embedded in the relationship between motion, inertia, and energy. At this point, it is tempting to rush ahead and connect everything explicitly to nuclear reactions or stars. But staying with light for a moment longer reveals something important. Light has no mass, yet it carries energy. It can exert pressure. It can transfer momentum. It can push on objects. This alone already blurred the line between energy and substance. If something without mass could carry momentum and affect matter, then the old categories were already weakening. Light did not fit neatly into the boxes of classical physics. It behaved like a wave, yet transferred energy in discrete packets. It moved at a universal speed. It ignored the motion of its source. These properties forced physicists to accept that c was not just a speed among others. It was a fundamental constant that structured reality. Once that acceptance settled in, the rest followed more naturally. If there was a maximum speed, then motion near that speed would behave differently. Energy near that speed would behave differently. Mass near that speed would behave differently. Even at everyday speeds far below c, the effects are present, but so small that they are negligible. This is why classical physics works so well in ordinary circumstances. The universe does not contradict itself. It layers behaviours, revealing deeper rules only when conditions demand them. The constancy of c is one of those deeper rules. It does not announce itself loudly. It simply refuses to be violated. It shows up in precise measurements, in the behaviour of particles, in the synchronization of clocks, and in the structure of equations. It quietly enforces consistency. As you sit and listen, you're surrounded by light that has travelled immense distances without changing speed. Photons from the sun left its surface about 8 minutes ago and arrived here without caring about the motion of the Earth, the rotation of the planet, or the speed of the atmosphere. That same constancy governs distant galaxies and laboratory experiments alike. This reliability is part of why the speed of light became so central. It is a fixed point in a universe that otherwise allows motion and variation, and once physics found that fixed point, it could build a new framework around it. That framework did not replace everything that came before, it extended it. Newtonian mechanics remained accurate at low speeds. Classical energy calculations remain useful, but beneath them lies a deeper unity, one that treats mass and energy as aspects of the same underlying reality. The appearance of c² in E equals mc² is a reminder of where this unity comes from. It comes from taking light seriously, from accepting that the universe enforces certain limits, and that those limits reshape how familiar quantities behave. For now, it is enough to stay with the idea that light forced physics to slow down and rethink its foundations. It exposed assumptions that had gone unnoticed because they worked too well, and in doing so, it prepared the ground for an equation that would eventually tie matter and energy together in a way that now feels inevitable, even though it once seemed unthinkable. Once the constancy of the speed of light had settled into physics, once it was accepted not as an experimental annoyance but as a foundational rule, a quiet shift began to take place in how other familiar ideas were interpreted. Among those ideas, mass was perhaps the most stubborn. For centuries, mass had been treated as one of the most basic properties an object could have. It was how much matter something contained. It determined how hard it was to push, how strongly it resisted acceleration, how much gravitational pull it exerted. Mass felt solid, literal, and beyond reinterpretation. And yet, when the new framework of relativity was allowed to fully unfold, mass no longer remained just a passive measure of how much stuff something was. It became something else. It became energy held in place. This idea is often stated quickly, almost casually, as if it were self-explanatory. Mass is energy. But that sentence hides more than it reveals. What does it actually mean for something solid, still, and seemingly inactive to be energy? Energy, after all, is usually associated with action, motion, heat, light, change. When you think of energy, you probably think of something happening. Mass, by contrast, feels like the opposite. It sits there, it persists, it does not announce itself. To understand how mass can be energy, it helps to let go of the everyday emotional meaning of the word energy and focus instead on how physics uses it. In physics, energy is not excitement or activity. It is not brightness or speed. Energy is a bookkeeping tool. It is a way of accounting for the ability of a system to change or to cause change. That ability does not need to be expressed constantly. It can exist quietly, stored, constrained, balanced by opposing forces. A stretched spring has energy even when it's not moving. A compressed gas has energy even when the container is still. A charged battery has energy even when it's sitting untouched on a shelf. In all of these cases, the energy is not visible as motion, but it is present as tension, structure, or configuration. Mass, it turns out, fits into this same category, just at a much deeper level. In the framework that leads to E equals mc², mass is not something separate from energy. It is a particular way energy appears when it's confined, stabilized, and prevented from dispersing. Mass is energy that has settled into a form that resists change. That resistance is what we experience as inertia. The heavier something is, the more energy is bound up in that stable configuration, and the harder it is to alter its state of motion. This reinterpretation does not contradict the older view of mass. It explains it. It tells us why mass behaves the way it does. When you push an object and it resists, it is not because it is stubborn or static by nature. It is because changing its motion requires interacting with the energy stored in its mass. Acceleration is not just a geometric change, it is an energetic one. The equation E equals mc² quantifies this idea. It tells us exactly how much energy corresponds to a given amount of mass. The answer is startling not because it introduces something exotic, but because the conversion factor is so large. The speed of a light is enormous, and squaring it makes it even larger. This means that even a small amount of mass corresponds to an enormous amount of energy. Not energy that is normally available, but energy that is fundamentally there. This is where misunderstandings often creep in. People hear that mass is energy and imagine that objects are secretly explosive, just waiting to be unleashed. That is not the case. The energy stored in mass is not accessible under ordinary conditions. It is locked in by the structure of matter itself. Releasing it requires processes that fundamentally rearrange or alter that structure. The reason mass can store so much energy has to do with how particles are held together. At the smallest scales, matter is not solid in the everyday sense. It is a dynamic arrangement of particles bound by forces. Those forces, whether electromagnetic or nuclear, involve energy. The stability of matter arises because these energies balance each other in precise ways. The total energy of that balanced system shows up from the outside as mass. In other words, mass is not an extra ingredient added on top of particles and forces. It is the energetic cost of holding those particles together in a stable configuration. If that configuration changes, the mass can change as well. This is not speculation. It is measured. It is observed. It is built into how physics accounts for reactions at fundamental levels. One of the most important consequences of this view is that mass is no longer absolutely conserved on its own. Instead, mass and energy together are conserved. In classical physics, these were separate rules. In relativistic physics, they merge into one. You can lose mass if you gain energy, and you can gain mass if you add energy. The total accounting remains balanced. This idea shows up in subtle ways long before it becomes dramatic. When a system releases energy, its mass decreases slightly. When a system absorbs energy, its mass increases slightly. These changes are usually far too small to measure in everyday situations, but they are real. A heated object weighs more than a cooler version of the same object by an unimaginably small amount. A compressed spring has slightly more mass than a relaxed one. A charged battery weighs more than a discharged one. These effects are not theoretical curiosities. They are direct consequences of E equals mc². They remind us that mass is not a static label, it is an energetic quantity. We simply do not notice the changes because the conversion factor is so large that ordinary energy exchanges barely register on the scale of mass. This perspective also changes how we think about rest. In classical physics, an object at rest had no kinetic energy. It could still have potential energy, but its rest itself carried nothing. In relativity, even an object completely at rest has energy. That energy is its rest energy. It's given by E equals mc². Motion adds more energy on top of that, but the baseline is never zero as long as mass is present. This means that rest is not emptiness. It is fullness held still. Every object, simply by existing, carries energy, not borrowed energy, not energy waiting to be activated, energy that is intrinsic to its mass. This does not make the world feel unstable. It makes it feel richer. The solidity of matter is not a lack of energy. It is energy arranged into persistence. It is also important to notice that this does not mean mass and energy are always interchangeable in practice. The equation tells you what could happen, not what easily happens. Accessibility matters. The energy stored in chemical bonds is far more accessible than the energy stored in nuclear bonds, which is far more accessible than the energy associated with mass itself. Each layer requires more extreme conditions to unlock. This layered structure is part of why the universe is stable enough for complexity. If mass energy were easy to release, stars would not shine steadily. Planets would not hold together. Life would not persist. The same equation that explains enormous energy potential also explains why it is usually locked away. Thinking of mass as stored energy also reshapes how we think about creation and destruction. In everyday language, we talk about creating energy or destroying matter. In physics, neither is quite accurate. Energy changes form, matter rearranges. At deeper levels, mass and energy flow into one another according to strict rules. Nothing disappears, nothing comes from nothing, it all transforms. This transformation does not require drama. It happens quietly in stars, where small changes in mass sustain light for billions of years. It happens in particle interactions, where energy concentrates into mass and then disperses again. It even happens, in principle, whenever energy is added to or removed from any system. The idea that mass is stored energy also dissolves the sense that matter is fundamentally inert. It is not dead weight filling space. It is structured activity. It is energy in equilibrium. This does not make a rock feel alive or dynamic in a mystical sense. It makes it intelligible. The rock behaves the way it does because of the energetic relationships that constitute it. Once this perspective is adopted, E equals mc² stops feeling like a strange claim and starts feeling inevitable. If energy can be stored in configurations, and if mass reflects resistance to change, then mass must correspond to energy. The equation simply tells us how much. Mass is not the opposite of energy. It is one of its quietest expressions. That realization does not demand excitement or urgency. It settles slowly, changing how familiar objects are understood without changing how they behave. The table remains a table. The body remains a body. But beneath their stillness lies an energetic story that physics now knows how to tell, patiently, consistently, and without spectacle. At first glance, the most intimidating part of E equals mc² is not the idea that mass and energy are connected. It is that little superscript, the square attached to the speed of light. People often accept that mass might relate to energy in some way, but then they see c² and feel the floor drop away. The number is so large that it feels disconnected from reality, as if it belongs to a different universe, where everyday intuition has no authority. Why square the speed of light at all? Why not simply multiply mass by c? Why does the equation insist on something so extreme? To understand why c² is so enormous, and why it has to be, It helps to move slowly away from the equation itself and toward the role speed plays in physics more generally. Speed is not just a measure of how fast something moves, it is a bridge between space and time. When you say something is moving at a certain speed, you are saying how much distance it covers per unit of time. Speed ties together two concepts that feel separate in daily life, but are deeply linked in physical description. In classical physics, speed appears in many energy-related formulas. Kinetic energy, the energy of motion, is given by 1/2 mass times speed squared. That squared term is not an accident. It reflects how energy grows as motion increases. If you double the speed of an object, you do not double its kinetic energy, you quadruple it. This is because energy accounts for how difficult it is to stop or change motion, not just how fast something is going. This squared relationship shows up again and again because energy is sensitive to change. Speed is already a rate. Squaring it emphasizes how rapidly energy escalates as motion increases. This is true for everyday objects and becomes dramatically true as speeds grow large. The speed of light enters the picture not as a convenient number, but as a fundamental limit. It is not just the speed at which light happens to travel. It is the maximum speed at which information, influence, or causal effects can propagate through the universe. Nothing with mass can reach or exceed it. This is not because of engineering constraints, but because of how space and time are structured. Once you accept that there is a maximum speed, that speed becomes a reference point for everything else. It sets the scale. It tells you how motion behaves when you approach that limit, and it turns out that energy increases without bound as you try to accelerate something closer and closer to that speed. In the relativistic framework, adding speed is not like stacking blocks. Each additional increment of speed requires more and more energy. As you approach the speed of light, the required energy grows so rapidly that reaching the limit becomes impossible. This behavior is not imposed artificially. It falls out of the geometry of space and time once c is fixed as a constant. Now consider what this means for an object at rest. Even when it is not moving, it exists within a universe that has this speed limit built into it. The same conversion factors that govern high-speed motion also govern rest. The energy associated with mass does not disappear simply because the object is still. It reflects the energy required to create and sustain that mass within a universe, where c sets the scale. This is where c² becomes unavoidable. The speed of light is the factor that converts between time-like quantities and space-like quantities. Squaring it ensures that energy, which has units involving both space and time, aligns correctly with mass, which resists acceleration in both spatial and temporal senses. Put differently, c² is not there to inflate the equation, it is there to make the units work out, and to reflect how deeply motion, inertia, and energy are intertwined. Without that squared term, the equation would not be consistent with how energy behaves at high speeds, or how mass responds to force. The enormity of c² is a consequence of how large the speed of light is compared to everyday speeds. We live in a slow corner of the universe. Cars, planes, even rockets move at speeds that are tiny fractions of c. Because of that, relativistic effects remain hidden in daily life. But the scale is always there, quietly governing what is possible. When you square the speed of light, you're squaring a number that is already enormous. This leads to a conversion factor that turns small amounts of mass into vast amounts of energy. That result often feels unsettling because it suggests power beyond comprehension. But it is important to remember that the equation is descriptive, not prescriptive. It tells you how much energy corresponds to mass, not how easily that energy can be released. The energy associated with mass is locked behind layers of stability. It is not like kinetic energy, which can be increased or decreased by pushing an object. It is not like chemical energy, which can be released by rearranging atoms. It is deeper than that. It is tied to the existence of mass itself. The reason c² is so large is precisely because mass is so stable. If the conversion factor were smaller, mass would not be as persistent. Objects would more readily lose mass when they emitted energy. The universe would behave very differently. Stars would burn out quickly, matter would be fragile, structure would be hard to maintain. The enormous value of c² ensures that mass is an exceptionally concentrated form of energy. That concentration is what gives matter its durability. It is what allows atoms to exist, molecules to form, and solid objects to remain intact over long periods of time. It is also worth noting that the speed of light is not large because the universe is extravagant. It is large because of how we define units. The meter and the second are human scale measurements. When you measure the speed of light in meters per second, you are comparing a fundamental cosmic limit to distances and times chosen for human convenience. The resulting number feels enormous because the units are small. If we defined distance and time differently, the numerical value of c would change, but the physics would not. What matters is not the number itself, but the fact that there is a fixed maximum speed and that it plays a central role in how energy and mass relate. Squaring c amplifies this role. It tells you that the connection between mass and energy is not a gentle one. It is steep. It is sensitive. Small changes in mass correspond to large changes in energy, because mass represents energy that is deeply bound. This steepness is what allows energy to be packed so densely into matter. It is also what makes mass such an effective source of gravity. Gravity in modern physics responds not just to mass, but to energy and momentum. The energy associated with mass contributes to how space and time curve. Without c² setting the scale, this curvature would not match observation. The appearance of c² also ensures consistency across different physical laws. Energy, momentum, and mass all transform in specific ways when observers move at different speeds. The speed of light governs these transformations. Squaring it aligns the relationship so that physical laws look the same to all observers, regardless of their motion. This consistency is crucial. Physics demands that its descriptions do not depend on arbitrary choices of reference frame. The same experiment performed in different states of motion must yield the same underlying results. The structure of relativity, with c at its center, guarantees this. The squared term is part of that guarantee. Another way to approach this is to think of c² as a measure of how much energy is required to give something mass. Creating mass is expensive, energetically speaking. Concentrating energy into a form that resists acceleration, persists over time, and contributes to gravity requires an enormous investment. The squared speed of light reflects that cost. This perspective can also be turned around. When mass disappears, even in tiny amounts, it releases an enormous amount of energy. This does not happen casually. It happens only when the conditions allow energy to escape from the configurations that normally hold it in place. The equation does not say that mass wants to become energy. It says that mass already is energy, held in a stable pattern. Releasing that energy means dismantling the pattern. The difficulty of doing so is why mass feels so solid and dependable. As you sit with this idea, it may begin to feel less dramatic and more explanatory. The enormity of c² is not an exaggeration. It is a reflection of how resistant mass is to change. It explains why mass behaves as a deep reservoir rather than a shallow pool. The universe needs such reservoirs. Without them, complexity would struggle to persist. Energy would disperse too easily. Structures would dissolve. The same constant that allows for extreme energy release under special conditions also ensures stability under ordinary ones. So when you see c² in the equation, it is not there to intimidate. It is there to encode the balance between stability and change. It tells you that mass is energy on a scale that makes it durable. That durability is not accidental. It is built into the fabric of space and time through the same constant that governs light. As this exploration continues, the focus will gradually shift toward what this enormous conversion factor means in practice. How it shows up in stars. How it appears in nuclear processes. how it shapes the evolution of the universe. But all of that rests on this simple, quiet fact. The speed of light sets the scale, and squaring it makes mass what it is. The size of c² stop feeling arbitrary. It is large because it must be. It is large because the universe demands both flexibility and endurance, and that balance, encoded in a single constant, threads its way through everything that follows. If you look around the room you're in right now, nothing about it feels extraordinary. There may be a table, a chair, a wall, perhaps a phone resting nearby, or a blanket folded at the edge of a bed. These objects feel settled. They feel finished. They feel like the opposite of anything dramatic. And yet, according to E=mc², every one of these ordinary things carries an amount of energy so vast that it is difficult to even put into words. Not energy in a practical sense, not energy you can access or feel, but energy that is genuinely there, woven into the very fact that the object exists at all. This is one of the most challenging ideas to truly absorb, not because it is complicated, but because it runs against how human intuition has been trained. We are very good at noticing energy when it is active. We feel heat when something is warm. We see light when something shines. We hear sound when something vibrates. Energy announces itself through change. Matter, on the other hand, announces itself through consistency. It stays. It resists being moved. It occupies space reliably. Our brains have learned to associate energy with activity and matter with stillness, and that association feels so natural that questioning it seems unnecessary. E=mc² asks you to loosen that association without discarding it. It does not say that everyday matter behaves like active energy. It says that everyday matter is energy in a deeply constrained form. The extraordinary potential is not visible because it is not meant to be. It is held in balance by the very same rules that allow matter to remain stable. To understand this without drifting into abstraction, it helps to think in layers. Energy appears at many levels, and each level has its own accessibility. At the most familiar level, you have mechanical energy. You push something, it moves. You lift something, it falls. This energy is easy to recognize and easy to release. One step deeper, there is chemical energy. Rearranging atoms releases or absorbs energy. This is the energy of food, fuel, and batteries. It is less obvious than motion, but still manageable with ordinary tools. Deeper still is nuclear energy, which involves rearranging the components inside atomic nuclei. This energy is far more concentrated and much harder to access. Beyond that lies the energy associated with mass itself. This is not stored in bonds that can be rearranged. It is bound up in the existence of the particles that make up matter. That is why it feels unreachable. It is not designed to be casually released. When people hear that a small amount of mass corresponds to an enormous amount of energy, the mind often jumps immediately to extremes. Explosions, destruction, power. But that reaction misses something important. The fact that matter contains extraordinary energy does not make the world unstable. It explains why it is stable. If that energy were easy to release, everyday objects would not remain intact. The universe would not be calm enough to support long-term structures. Think about how long ordinary matter lasts. Rocks persist for millions of years. Mountains erode slowly. Buildings stand for decades or centuries. Even fragile objects remain intact unless acted upon. This persistence is not accidental. It is a sign that the energy bound into matter is extremely well locked away. The extraordinary potential is precisely what gives rise to extraordinary durability. This also explains why the mass of everyday objects seems so unaffected by changes in energy at ordinary scales. When you heat a cup of water, you add energy. When it cools, energy leaves. According to E=mc², the mass of the water changes slightly as this happens. But the change is so small that it is utterly undetectable without extraordinary precision. The conversion factor, c², is so large that even noticeable energy exchanges barely register as changes in mass. This is not a flaw or a limitation, it is a feature. It allows energy to flow freely at everyday scales without destabilizing matter. It allows systems to heat and cool, move and rest, without changing what they are in any noticeable way. The extraordinary energy associated with mass remains in the background, maintaining structure rather than disrupting it. One way to gently feel this idea is to think about how much energy it would take to create matter from nothing, if that were possible. Creating even a tiny amount of mass would require an enormous concentration of energy. The universe does not do this casually. It does it under extreme conditions, such as in the early moments after the beginning of cosmic expansion, or in high-energy particle interactions. Everyday environments simply do not provide the necessary conditions. This tells you something important about ordinary objects. They are not cheap. Energetically speaking, they represent an immense investment. The fact that they exist at all means that the universe has already paid that energetic cost and then arranged the result into stable configurations that can persist. This perspective can subtly change how matter feels, not in an emotional or mystical way, but in an explanatory one. A table is not just wood arranged into a flat surface. It is energy that has been shaped, cooled, and stabilized over cosmic timescales. The atoms within it were forged in stars. The particles within those atoms emerged from even earlier processes. The energy that defines their mass has been present since the universe settled into its current rules. None of this requires imagining the table as glowing or active. It simply requires recognizing that stillness does not imply emptiness. Stability does not imply lack of energy. It implies balance. The extraordinary potential remains hidden because it is balanced by forces that prevent it from expressing itself. This balance is maintained through fundamental interactions. Particles are held together by forces that themselves involve energy. These forces are not external constraints. They are part of the same energetic accounting that gives rise to mass. The result is a self-consistent system where energy organizes itself into forms that persist. It is also worth noticing that this extraordinary potential is not evenly distributed. Different forms of matter have slightly different masses depending on their internal energy configurations. When atoms bind together into molecules, a small amount of energy is released, and the mass of the resulting molecule is slightly less than the sum of the masses of the separate atoms. This difference is known as binding energy, and it is another quiet expression of E equals mc² at work. Again, these mass differences are incredibly small. They do not affect how objects feel or behave at human scales, but they are real, measurable, and consistent. They remind us that mass is not a fixed label, but a reflection of energetic relationships. This idea also helps resolve a common misunderstanding. When people hear that mass is energy, they sometimes imagine that energy must therefore be material, that it must have substance. But energy is not a thing in the way matter is. It is a property of systems. Mass is not energy turned into stuff. It is energy expressed as resistance to change within a particular configuration. Everyday matter feels ordinary precisely because its extraordinary potential is not trying to go anywhere. It is settled. It is content to remain as it is unless forced otherwise. That contentment is what allows complexity to exist. Life, technology, and long-term structures all rely on the fact that matter does not spontaneously release its deepest energy. If this were not the case, the universe would be unrecognizable. Stars would not shine steadily. They would flare and vanish. Planets would not hold together. Chemistry would not be predictable. The same equation that implies enormous energy also implies restraint. This restraint is not imposed from outside. It arises from the same rules that relate mass, energy, space, and time. The extraordinary potential of matter is inseparable from its ordinary behavior. They are two sides of the same relationship. As you move through daily life, you do not need to think about this. The world works without your attention, but understanding it adds depth to familiar surroundings. It replaces the idea of matter as inert with the idea of matter as settled energy. Not dormant, not waiting, simply balanced. This balance is dynamic at microscopic scales, but it appears static at human ones. Particles vibrate, fields fluctuate, forces interact, yet the overall configuration holds. That is what mass represents. Not frozen energy, but energy whose movements cancel out in a way that produces persistence. This also means that everyday matter is not separate from the grander story of the universe. The same principles that govern stars and galaxies govern your surroundings. The difference is not in the rules, but in the scale at which they express themselves. It is enough to stay with the contrast itself. Ordinary matter, extraordinary potential. Not as a contradiction, but as a pairing. The world around you is calm because the energy within it is balanced. The equation does not ask you to fear that energy. It asks you to understand why it stays where it is. And as that understanding settles, the objects around you do not change. But the story they belong to grows deeper. When people first hear that E equals mc² explains how stars shine, it often sounds like an exaggeration, as if a single equation is being given too much credit. Stars feel vast, distant, and complex. An equation feels small and human. But the connection is real, and it is not dramatic in the way explosions are dramatic. It is steady, patient, and unfolding over immense spans of time. The light that reaches your eyes from the sun each day is not just warmth or brightness. It is the visible expression of mass quietly becoming energy, written across the sky in a language the universe has been using for billions of years. To appreciate this, it helps to begin not with stars but with the problem they once posed. For a long time, scientists did not understand how the sun could keep shining. Measurements showed that it had been emitting enormous amounts of energy for a very long time. Geological evidence suggested that the Earth was billions of years old. Biological evidence suggested the same, yet known energy sources at the time could not account for this. If the sun were burning chemical fuel, like a giant fire, it would have exhausted itself in a few thousand years. If it were slowly contracting under gravity and releasing energy that way, it might last a few tens of millions of years, but not billions. This mismatch was deeply troubling. The sun was stable. Its output was steady. Life depended on that steadiness, but no classical explanation could sustain it for the required timescale. Something fundamental was missing. The answer did not arrive all at once. It emerged gradually as physics began to understand the structure of atoms and the forces within them. At the centre of this understanding was the realization that atomic nuclei were not indivisible points, but structured systems held together by powerful forces. Those forces involved energy, and crucially the total mass of a nucleus was not simply the sum of the masses of its parts. When lighter nuclei combine to form heavier ones, the resulting nucleus often has slightly less mass than the original components. That missing mass does not vanish. It appears as energy. This is not metaphorical, it is literal. The difference in mass multiplied by c² gives the amount of energy released. In the core of the Sun, this process happens continuously. Hydrogen nuclei combine through a series of steps to form helium. Each step involves a small loss of mass and a corresponding release of energy. The amount of mass lost in each reaction is tiny, far too small to notice in isolation. But the Sun contains an enormous amount of hydrogen, and these reactions occur in vast numbers every second. The cumulative effect is what we see as sunlight. This is where E equals mc² becomes tangible. The Sun is not burning fuel in the everyday sense. It is converting mass into energy slowly and efficiently. The squared speed of light ensures that even a small amount of mass can sustain enormous energy output over long periods. The Sun does not need to lose much mass to shine brightly. Over billions of years, it loses only a small fraction of its total mass, yet that loss powers the entire solar system. When sunlight reaches the Earth, It carries with it the imprint of this process. Each photon began its journey deep within the Sun, produced by a nuclear reaction that converted mass into energy. That photon may have taken thousands of years to work its way to the surface, bouncing between particles, being absorbed and re-emitted countless times. Once it escaped, it travelled through space at the speed of light, arriving here about 8 minutes later. When that light warms your skin or illuminates a room, you are directly experiencing E equals mc². Not as a calculation, not as a concept, but a sensation. The warmth is energy. The light is energy. And that energy exists because mass was transformed at the heart of a star. This realization changes how stars are understood. They are not just glowing balls of gas. They are engines of mass-energy conversion, governed by precise balances. Gravity pulls material inward, nuclear reactions push outward. When these forces balance, a star remains stable. When the balance shifts, the star evolves. The remarkable thing is how controlled this process is. Stars do not explode constantly. They shine steadily for millions or billions of years. This stability depends on the same enormous conversion factor that makes E equals mc² feel intimidating. Because c² is so large, only a small fraction of mass needs to be converted to sustain immense energy output. This allows stars to burn slowly rather than violently. Different stars follow different paths depending on their mass. Smaller stars burn fuel slowly and can shine for tens or even hundreds of billions of years. Larger stars burn fuel more rapidly, shining brighter but living shorter lives. In all cases, the underlying process is the same. Mass is being converted into energy according to E equals mc². The Sun sits comfortably in the middle. It is massive enough to sustain nuclear fusion, but not so massive that it burns itself out quickly. This balance is part of why life on Earth is possible. The steadiness of sunlight allows climates to stabilize, ecosystems to develop, and biological processes to persist over long timescales. It is worth pausing here to appreciate how indirect this connection feels. When you step outside on a clear day, you do not think about nuclear fusion. You think about warmth, brightness, perhaps the comfort of light after darkness. Yet all of that depends on processes that convert mass into energy at the core of a star you cannot see directly. The equation does not diminish that experience, it deepens it. It tells you that the light feels gentle because the conversion is gentle. It tells you that the sun shines steadily because mass is an extraordinarily concentrated form of energy. The enormity of c² ensures longevity rather than chaos. This same process writes patterns across the night sky. Every star you see is engaged in some form of mass energy conversion. Their colours tell you about their temperatures and the types of reactions occurring within them. Their brightness tells you about their size and energy output. Their lifetimes tell you how quickly they convert mass into energy. Even the elements that make up your body were forged through these stellar processes. Heavier elements are created in the cores of stars or during their violent deaths. In those moments, mass-energy relationships play out on dramatic scales. New forms of matter emerge as energy flows and reorganizes. The periodic table itself is a record of how mass and energy interact over cosmic time. When people say that we are made of star stuff, they are not being poetic, they are being literal. The atoms in your body owe their existence to processes governed by E equals mc². The energy that once powered stars helped create the matter that now makes you. This connection does not require awe or reverence to be meaningful. It is simply explanatory. It shows how the same rules apply everywhere. The sun is not special because it is near. It follows the same laws as distant stars. The Earth is not special because it hosts life. It depends on the same energy flows that shape galaxies. Understanding this also clarifies why stars eventually change. As hydrogen fuel is used up, the balance between gravity and energy shifts. New reactions begin. The structure of the star evolves. Mass continues to convert into energy, but in different ways. The life cycle of a star is essentially a story about how mass-energy conversion unfolds under changing conditions. At the end of some stars' lives, the process becomes far more dramatic. Supernovae release enormous amounts of energy in short periods. In those moments, mass-energy conversion is no longer gentle. Large amounts of mass are transformed rapidly. The brightness of such events can briefly outshine entire galaxies. Yet even here, the same equation applies. The difference is not in the rules, but in the circumstances. These extreme events are rare and distant. The everyday experience of starlight is not one of violence, but of consistency. Night after night, stars hold their positions. Their light reaches us unchanged by our motion, steady and reliable. This steadiness is not accidental. It is the outcome of precise balances governed by fundamental constants. Sunlight, in particular, is easy to take for granted. It arrives without effort. It defines day and night. It sets rhythms in plants and animals. But beneath that familiarity lies a process that converts mass into energy with extraordinary efficiency and restraint. E equals mc² is not a distant abstraction here. It is the reason mornings are bright. Even after light leaves the sun, the equation continues to matter. Light carries energy and momentum. It exerts pressure. It can push on matter. Over long periods, radiation pressure influences the behavior of dust and gas in space. Energy flows shape the formation of stars and planets. Mass-energy relationships guide the architecture of cosmic systems. When you look up at the sky, especially at night, it is easy to feel small. Vast distances and immense scales can make human concerns feel insignificant. But understanding the physics behind starlight offers a different perspective. The same equation that governs distant stars also governs the mass of objects around you. The same constant that sets the brightness of the sun sets the stability of matter in your surroundings. This continuity is one of the quiet strengths of physics. It does not divide the universe into separate realms of everyday life and cosmic phenomena. It uses the same principles everywhere. E equals mc² does not belong only to textbooks or laboratories. It belongs to the sky above you and the light that fills your days. As this exploration continues, attention will gradually move from stars themselves to the broader implications of mass-energy conversion, how it shapes the evolution of the universe as a whole, how it influences time, gravity, and the structure of space. But all of those larger ideas rest on this simple, steady fact. Stars shine because mass becomes energy. That fact does not demand excitement. It does not require you to imagine extremes. It simply asks you to notice that the warmth and light you experience are part of a much deeper accounting. The equation is written in the sky not as symbols, but as illumination, arriving quietly, moment after moment, without ever needing to announce the mathematics behind it. There are moments when an idea that usually stays hidden suddenly steps into view. For E equals mc², nuclear energy is one of those moments. Most of the time, the relationship between mass and energy is so subtle that it goes unnoticed. Objects stay the same size. Their mass feels constant. Energy comes and goes without leaving a mark you can weigh or measure. Nuclear processes change that. They pull back the curtain just enough for the equation to stop being theoretical and start being observable. To understand why this happens, it helps to return to the structure of matter itself. Atoms, despite how solid they feel in large numbers, are mostly empty space. Their mass is concentrated in tiny nuclei at the center, surrounded by electrons. Those nuclei are made of protons and neutrons, particles packed together incredibly tightly. Holding them together is the strong nuclear force, one of the most powerful interactions known in physics. It operates over very short distances, but within those distances it dominates everything else. This force is not gentle. It requires energy to overcome it, and it releases energy when configurations change. The way protons and neutrons arrange themselves inside a nucleus determines how much energy is involved. Some arrangements are more stable than others. When a nucleus shifts from a less stable configuration to a more stable one, energy is released. Crucially, the mass of the final nucleus is slightly less than the mass of the initial components. The missing mass has not vanished. It has become energy. This is the point where E=mc² moves from a quiet background principle to an accounting tool you can actually use. In nuclear reactions, the mass difference is small, but not unimaginably small. It is large enough to measure. Multiply that difference by c², and you get an amount of energy that matches what is released. The equation does not approximate, it balances exactly. There are two main ways nuclear energy appears. One is nuclear fusion, where light nuclei combine to form heavier ones. This is what happens in stars. The other is nuclear fission, where heavy nuclei split into lighter ones. This is what happens in nuclear reactors and weapons. In both cases, the key idea is the same. The final products have less mass than the starting materials, and the difference appears as energy. What makes nuclear energy feel so different from other forms of energy is the scale. Chemical reactions rearrange electrons. Nuclear reactions rearrange nuclei. The energies involved are separated by orders of magnitude. A chemical reaction might release energy you can feel as heat or light. A nuclear reaction releases energy that can power cities or alter landscapes. Yet the underlying principle is the same. Energy is released when systems move toward more stable configurations. This is where everyday intuition often struggles. People tend to think of mass as something that should always be conserved. Losing mass feels like losing substance. In nuclear reactions, that intuition has to be updated. The system does not lose anything. It trades mass for energy. The total accounting, when done properly, remains balanced. This balance is not optional. It is enforced by the structure of physical law. If nuclear reactions released energy without losing mass, conservation would fail. If mass disappeared without producing energy, the universe would not add up. E=mc² is what ensures consistency. Nuclear reactors provide a controlled environment where this conversion happens slowly and predictably. Fuel rods contain materials like uranium, whose nuclei can split under the right conditions. When a nucleus splits, it releases energy and additional particles that can trigger further reactions. Control systems manage this chain reaction, allowing energy to be released at a steady rate. The electricity generated by a nuclear power plant ultimately comes from this mass-energy conversion. Heat produced by nuclear reactions turns water into steam. Steam turns turbines. Turbines generate electricity. At the end of this long chain, the original source of the energy is still E=mc². A tiny reduction in mass produces a usable amount of energy. What is striking is how little mass is actually involved. A nuclear power plant can operate for years while consuming only a small amount of fuel. The mass difference between fresh and spent fuel is almost impossible to detect without sensitive instruments. Yet the energy produced is enormous. This contrast makes the equation feel real in a way few other contexts do. Nuclear weapons represent the same process without restraint. In these devices, nuclear reactions are allowed to proceed extremely rapidly. Large amounts of mass are converted into energy in fractions of a second. The result is an explosion of light, heat, and force that is unmistakable. Here, E=mc² is not subtle, it is overwhelming. It is important to approach this topic calmly and clearly. The existence of nuclear weapons does not change the nature of the equation, it changes the conditions under which it is applied. The same relationship governs the gentle glow of a reactor core and the destructive power of a bomb. The difference lies in control, scale, and intent. This distinction matters because it shows that the equation itself is not dangerous. It is descriptive. It tells you what happens when mass changes. How that knowledge is used depends on choices made far outside the realm of physics. In many ways, nuclear energy is unsettling precisely because it reveals something that usually stays hidden. It shows that matter is not as immutable as it feels. Under the right conditions, mass can change, and when it does, the effects are dramatic. This challenges the everyday sense of solidity that people rely on. Yet even here, stability dominates. Nuclear reactions do not happen spontaneously in everyday environments. Atomic nuclei are extraordinarily stable under normal conditions. They require precise circumstances to change. This stability is another reflection of the enormous value of c². It makes mass an extremely concentrated form of energy, difficult to access. The visibility of E equals mc² in nuclear processes also helps clarify a common misconception. People sometimes imagine that nuclear energy comes from the annihilation of matter. That is not accurate. Most nuclear reactions involve partial conversion. Only a small fraction of mass is converted into energy. The rest remains as matter in a different configuration. Complete conversion of mass into energy does occur in certain particle-antiparticle interactions, but those are rare and require very specific conditions. Even there, the equation holds exactly. All the mass becomes energy, and the amount released matches the prediction. Seeing the equation at work in nuclear energy also reinforces an important lesson about scale. At human scales, mass feels fixed. At atomic scales, it is slightly flexible. At subatomic scales, it is deeply intertwined with energy. Physics does not contradict itself across these scales. It reveals different layers of the same rules. This layered understanding is what allows nuclear energy to be both comprehensible and controllable. Engineers do not need to abandon classical physics to build reactors. They incorporate relativistic insights where they matter and rely on classical approximations where they are sufficient. The equation integrates seamlessly into a broader framework. There is also a psychological dimension to this visibility. Knowing that ordinary matter contains extraordinary energy can be unsettling. It can make the world feel fragile. But the opposite is true. The fact that this energy remains locked away under normal conditions is what makes the world robust. Nuclear energy is visible precisely because special conditions have been created to reveal it. This perspective can help reframe fear into understanding. The equation does not turn the world into a ticking clock. It explains why it is not one. The same principles that allow for nuclear energy also prevent it from being released accidentally. The universe enforces its rules consistently. As nuclear energy became visible in the 20th century, it reshaped technology, politics, and culture. But it did not change the equation. It confirmed it. Measurements of nuclear reactions matched predictions with extraordinary accuracy. Each successful calculation reinforced the idea that mass and energy are two sides of the same accounting system. That confirmation extended beyond Earth. Observations of stellar processes, supernovae, and cosmic radiation all aligned with the same framework. The equation proved itself across environments that could not be more different. Understanding nuclear energy as the visible face of E equals mc² helps bridge the gap between abstract theory and lived reality. It shows that the equation is not just a line on a page, it is a rule that governs how the universe behaves when pushed to its limits. It is enough to sit with the idea that nuclear energy is not an exception. It is a demonstration. It is what happens when the quiet relationship between mass and energy becomes visible enough for human instruments to detect. The equation has always been there. Nuclear processes simply make it impossible to ignore. For a long time, the words creation and destruction carried very specific meanings in science. To create something meant to bring it into existence. To destroy something meant to eliminate it entirely. These ideas feel natural because they match everyday language and experience. You build a chair, you burn a piece of paper, one thing appears, another disappears. Yet as physics has slowly refined its understanding of the universe, those words have had to soften. They have not vanished, but they no longer mean quite what they once did. And nowhere is that shift clearer than in the way mass and energy are treated together. Before E equals mc² entered the picture, conservation laws were cleanly divided. Matter was conserved. energy was conserved. They were tracked separately, like two ledgers that never intersected. You could destroy a structure, but not the matter it was made of. You could release energy, but not eliminate it. This framework worked remarkably well, and it shaped how scientists spoke about processes. Creation and destruction were practical terms, not absolute ones. You could create energy in a power plant. You could destroy energy through friction. Everyone understood that this was shorthand, not literal disappearance, but the language stuck. Once mass and energy were understood as interchangeable, even in principle, those words became more slippery. If mass could become energy, and energy could become mass, then what exactly was being created or destroyed? The answer, quietly and consistently, was nothing. The universe was not losing or gaining substance. It was rearranging how substance was expressed. This is where conservation takes on a deeper meaning. Conservation is not about freezing the universe in place. It is about maintaining balance across change. When something seems to vanish, it reappears in another form. When something seems to appear, it has been drawn from elsewhere. E equals mc² is one of the equations that ensures this balance holds even when familiar categories break down. Consider nuclear reactions again, but this time focus not on their power, but on their accounting. When a nucleus splits or fuses, the total mass of the products is different from the total mass of the reactants. If you only track mass, it looks as if matter has been destroyed or created. But if you track energy as well, the discrepancy disappears. The missing mass shows up as energy, or added energy shows up as additional mass. The total remains consistent. This consistency is not an optional feature. It is built into the structure of physical law. The universe does not tolerate imbalances. Every process that appears to create or destroy something is, at a deeper level, a transformation. Conservation laws are the bookkeepers that make sure nothing slips through unnoticed. This idea also reshapes how beginnings and endings are understood. In everyday life, things begin and end constantly. A fire starts, a fire goes out, a living organism is born, a living organism dies. These events feel final, yet in physical terms they are transitions. Matter and energy rearrange, patterns change, structures dissolve or form, but the underlying constituents continue. E equals mc² extends this principle to mass itself. It tells you that even when matter seems to disappear, it does not leave the universe, it becomes energy. And when energy seems to condense into matter, it has not come from nothing, it has taken on a new role. This perspective is especially important when thinking about the early universe. In the moments after cosmic expansion began, conditions were extreme. Energy densities were enormous. Temperatures were unimaginably high. Under those conditions, energy could condense into particles. Matter was not created from nothing. It emerged from energy according to the same accounting rules that apply today. As the universe expanded and cooled, these processes slowed. Matter became more stable. Energy spread out. The balance shifted, but conservation remained intact. The universe did not gain substance. It redistributed it. This also means that destruction, in the absolute sense, does not occur in physics. You can destroy a structure, you can destroy an arrangement, you can destroy usefulness or function, but you cannot destroy mass energy itself. It persists through every transformation. This idea can feel abstract, but it shows up in very concrete ways. When fuel burns, chemical energy becomes heat and light. The mass of the system decreases by an amount too small to measure easily. When an object cools, it loses energy and therefore mass. These changes are real, even if they are negligible at human scales. What E equals mc² does is close a loophole that once existed in conservation thinking. It ensures that energy conservation and mass conservation are not separate rules that sometimes conflict. They are aspects of a single principle. Together, they describe how the universe keeps its accounts balanced. This unified conservation has philosophical implications, but it does not require philosophical language to be meaningful. It simply means that the universe is economical. It does not throw things away. It does not conjure things without cost. Everything that happens fits within a consistent framework. Creation then becomes a matter of arrangement. When something new appears, it has been assembled from existing components. Those components carry energy. The process of assembly redistributes that energy. Sometimes energy is released, sometimes energy is absorbed, but the total remains. Destruction becomes disassembly. When something breaks down, its components persist. Their energy persists. What changes is the pattern, the usefulness, the form, the story we tell about it. This perspective can be surprisingly calming. It removes the sense that things are ever truly lost. In physical terms, they are not. The atoms that make up a body return to the environment. The energy that once animated processes dissipates into heat and radiation. Nothing disappears. It spreads. E equals mc² ensures that even the most extreme processes follow this rule. In particle collisions, matter can appear to annihilate. A particle meets its antiparticle. Both vanish. What remains is energy in the form of radiation. Again, nothing is lost. The masses become energy exactly as the equation predicts. This exactness matters. It tells you that the equation is not a metaphor. It is not a poetic statement about equivalence. It is a precise rule that holds in every tested scenario. The universe obeys it with no exceptions observed so far. Understanding this helps resolve confusion around terms like mass loss and energy release. When a system releases energy, it loses mass. When it absorbs energy, it gains mass. These statements are not approximations. They are literal. They simply operate at scales that are usually too small to notice. This also explains why mass is often treated as constant in everyday calculations. The changes are so small relative to the mass involved that they can be ignored without consequence. Classical physics remains an excellent approximation because the universe is generous with stability. Relativity refines the picture without invalidating it. Creation and destruction also take on new meaning when applied to cosmic scales. Stars form, stars die, galaxies collide, structures emerge and dissolve. Through all of this, mass energy flows according to consistent rules. Nothing breaks the accounting. Even black holes, often thought of as ultimate destroyers, do not violate conservation. They absorb mass and energy. Their mass increases accordingly. When they emit radiation through quantum processes, their mass decreases. The balance holds. This is important because it reinforces the idea that E equals mc² is not an isolated insight. It fits into a network of principles that describe how reality behaves. It supports conservation rather than undermining it. It explains apparent violations by revealing deeper consistency. In everyday language, creation and destruction are useful terms. They help us describe change. But physics invites us to see beyond them. It asks us to notice continuity beneath transformation. E equals m² is one of the tools that makes that continuity visible. This does not mean that change is insignificant. On the contrary, change is everything. It is how patterns form, evolve, and dissolve. But change happens within constraints. Conservation is one of those constraints. It gives the universe structure. Nothing truly vanishes. Nothing truly appears from nowhere. Mass and energy move, transform and reorganize, but they are never lost. The equation does not strip the universe of mystery. It gives that mystery boundaries. Those boundaries are what make understanding possible. They allow us to trace connections across scales, from nuclear reactions to stellar life cycles to the quiet persistence of everyday matter. And within those boundaries, the universe continues to change endlessly without ever losing itself. When the equation E equals mc² is first encountered, it is usually framed as a statement about objects, reactions, or processes. Mass here, energy there, a conversion between the two. But as physics continued to absorb what this relationship actually implied, it became clear that the equation was not only about things within the universe, it was also about the universe itself, its structure, its behaviour on the largest scales, the way space and time respond to what exists inside them. Slowly, almost reluctantly, E equals mc² revealed that it was woven into the shape of the cosmos. To see how this happens, it helps to step away from stars and particles for a moment and think about gravity. For most of human history, gravity was understood as a force acting between masses. Objects with mass attracted one another. The more mass, the stronger the attraction. This idea works extremely well for everyday situations and even for planetary motion. It allows you to calculate orbits, predict tides, and send spacecraft across the solar system with remarkable accuracy. But gravity, as Einstein eventually showed, is not just a force pulling objects together. It is a manifestation of how mass and energy influence space and time themselves. Space is not a rigid stage. Time is not an independent ticking background. Together they form a unified structure, often called space-time, and that structure responds to what is inside it. This is where the equation quietly expands its reach. If mass is a form of energy, then gravity cannot respond only to mass, it must respond to energy as well. And not just energy in the form of motion or radiation, but energy in all its forms: heat, pressure, momentum. Even energy that appears completely still contributes to how space-time is shaped. In this framework, the shape of the universe is not determined solely by how much matter it contains, but by how much mass energy it contains in total. E equals mc² ensures that mass contributes enormously to this total, even when it is not doing anything dramatic. Imagine space-time as a flexible structure that adjusts itself based on what exists within it. Add mass energy and space-time curves. Change how that mass energy is distributed, and the curvature changes. This curvature tells objects how to move. Objects follow paths determined not by invisible forces, but by the geometry of space-time itself. This idea can feel abstract, but its consequences are concrete. Light bends near massive objects. Time runs at different rates depending on gravitational strength. Orbits exist because space-time is curved, not because planets are being pulled through empty space by mysterious threads. E equals mc² matters here because it tells you how much mass energy is present, even when that energy is locked into matter at rest. A planet curves space-time not just because it is heavy, but because its mass represents a vast amount of energy concentrated into a stable form. On the scale of the entire universe, this becomes even more important. Cosmology, the study of the universe as a whole, depends critically on how much mass energy exists and how it is distributed. The expansion of the universe, its past, and its future are all tied to this accounting. When astronomers measure the motion of galaxies, they find that the universe is expanding. Galaxies are moving away from each other, not because they are flying through space like debris from an explosion, but because space itself is stretching. This expansion is influenced by the total mass energy content of the universe. If the universe contains enough mass energy, gravity can slow the expansion, possibly even reverse it. If it contains too little, expansion continues indefinitely. If different forms of energy behave differently, the expansion can accelerate or decelerate in complex ways. Here again, E equals mc² is not a side note, it is central. It tells cosmologists how to convert between different contributions to the universe's energy budget. Matter contributes, radiation contributes, energy associated with fields contributes, even energy that does not cluster into matter contributes. Early in the universe's history, energy dominated over mass in familiar forms. Temperatures were high, particles moved rapidly, radiation filled space densely. As the universe expanded and cooled, energy spread out, matter became more prominent, structures formed, galaxies emerged. Throughout this evolution, mass energy conservation held. Energy transformed into matter, matter transformed back into energy. The balance shifted, but the total accounting remained consistent. One of the most striking implications of this is that the universe's geometry depends on its energy density. If the energy density is above a certain critical value, space-time is curved in one way. If it is below, it curves in another. If it matches exactly, space-time is flat on large scales. Measurements suggest that the universe is remarkably close to this critical balance. On the larger scales we can observe space-time appears nearly flat. This fact has profound implications for cosmology and for our understanding of the early universe. Again, E equals mc² underlies these conclusions. Without a clear understanding of how mass and energy relate, it would be impossible to translate observations of light, motion, and structure into statements about the universe's shape. The equation also plays a role in understanding cosmic horizons. Because energy influences space-time, and space-time determines how light travels, the distribution of mass-energy limits what parts of the universe can influence one another. There are regions beyond which light has not had time to reach us. These horizons are not arbitrary. They arise from the interplay between expansion, energy density, and the speed of light. Even emptiness is affected. What we call empty space is not devoid of energy. Quantum fields contribute energy even in the absence of particles. This energy, sometimes called vacuum energy, also curves space-time. It affects the universe's expansion rate. It plays a role in what is often referred to as dark energy. Once again, E equals mc² provides the translation. Energy, regardless of its form, contributes to the universe's gravitational behavior. Whether that energy is locked into matter, moving as radiation, or present as a property of space itself, it enters the same accounting. This unified view replaces an older picture in which matter shaped the universe and energy merely acted within it. Instead, everything that carries energy participates in shaping space-time. The universe responds not to labels but to quantities. This also means that the universe's fate is not determined solely by visible matter. Invisible forms of energy matter just as much. Their presence or absence influences expansion, structure formation, and long-term behavior. From this perspective, E equals mc² becomes part of cosmology's foundation. It is not a separate insight about reactions or stars. It is a principle that allows the universe to be treated as a coherent physical system. Even the idea of a beginning is shaped by this relationship. The early universe was a state of extremely high energy density. Under those conditions, energy condensed into particles. Mass emerged as the universe cooled. This was not creation from nothing, but transformation under extreme conditions. As time progressed, mass energy became distributed unevenly. Gravity amplified small fluctuations. Structures grew, galaxies formed, stars ignited. All of this unfolded according to how mass energy curved space-time and how space-time guided motion. The equation does not explain why the universe exists. It explains how it behaves once it does. It tells you how content and geometry interact. It ensures consistency between what exists and how it shapes the arena it occupies. This consistency is what allows cosmology to be predictive. By measuring how galaxies move and how light travels, scientists infer the universe's energy content. By understanding that content through E equals mc², they infer the universe's shape and evolution. None of this requires imagining the universe as fragile or precarious. On the contrary, it reveals deep stability. The same principles that govern a single particle govern the entire cosmos. The same accounting that balances a nuclear reaction balances cosmic expansion. As you let this idea settle, the equation may begin to feel less like a statement about conversion and more like a statement about unity. Matter, energy, space, and time are not separate compartments. They are aspects of a single interconnected system. This interconnectedness does not erase distinctions. Matter still behaves differently from radiation. energy still takes many forms. But beneath those differences lies a common currency, one that space-time responds to consistently. E equals mc² does not stop at objects or reactions. It reaches outward, shaping the very geometry of the universe. It links what exists to how existence is arranged. And in doing so, it becomes less about calculation and more about structure, quietly holding the cosmos together as it expands, evolves, and continues on its long, unhurried path. There comes a point, once mass and energy have been woven together, and once their influence on the shape of the universe has been acknowledged, where attention naturally drifts toward the quiet backdrop everything seems to unfold against: time, space. These two ideas feel so familiar that they rarely invite scrutiny. Time feels like something that passes. Space feels like something things sit inside. For most of human history, they were treated as separate, absolute, and unquestionable. Events happened in space. They unfolded in time. Physics described what moved where and when, and that seemed sufficient. Yet once E equals mc² entered the picture, once energy, mass, and gravity became deeply linked, time and space could no longer remain untouched. They, too, had to be reconsidered. Before relativity, time was assumed to flow at the same rate everywhere. A second was a second, regardless of where you were or how you moved. Space was assumed to be rigid and unchanging, a fixed stage on which the universe played out its story. You could choose different coordinate systems, but the underlying structure was assumed to be the same for everyone. This assumption worked beautifully for everyday motion, and even for celestial mechanics. Planets followed predictable paths. Clocks could be synchronized. The universe felt orderly and dependable. The strange behavior of light disrupted this comfort. If the speed of light was the same for all observers, regardless of their motion, then something had to give. Speeds could no longer simply add up. Observers moving relative to one another could not agree on how fast time passed or how long objects were. This was not a philosophical issue, it was a mathematical necessity imposed by experimental results. Einstein's insight was not to invent new behavior, but to accept what nature was already telling him. He took the constancy of the speed of light seriously and followed it to its logical conclusions. Those conclusions were unsettling because they challenged deeply held intuitions about time and space, but they were also remarkably consistent. In this new framework, time and space were no longer independent. They were aspects of a single structure. Events were not located at a position and a moment separately. They were located in space-time. Different observers, moving relative to one another, slice space-time into space and time differently. What one observer called simultaneous, another might not. What one observer measured as a longer duration, another might measure as shorter. This is where E equals mc² quietly underpins the entire structure. Energy and mass influence how space-time behaves, and space-time, in turn, governs how energy and mass move. The equation does not float above relativity. It is embedded within it. One of the most counterintuitive consequences of this framework is time dilation. When an object moves at high speed relative to an observer, time passes more slowly for that object as seen by the observer. This is not an illusion. It is not a trick of perception. It is a measurable effect. Clocks in motion tick more slowly than clocks at rest, relative to a given frame of reference. This effect becomes dramatic only at speeds approaching the speed of light. At everyday speeds it is negligible, but it is always present. The universe does not turn it on and off. It applies it consistently. Length contraction accompanies time dilation. Objects moving at high speed appear shorter in the direction of motion relative to an observer. Again, this is not because objects physically compress in their own frame. It is because space and time are being partitioned differently by different observers. These effects often sound like curiosities until they are connected back to energy and mass. As an object moves faster, its energy increases. This energy increase is not just kinetic energy in the classical sense. It reflects a deeper relationship between motion and mass energy. The more energy an object has, the harder it is to accelerate further. As speed increases, additional energy contributes less to speed and more to inertia. This is why objects with mass cannot reach the speed of light. Doing so would require infinite energy. That infinite energy would correspond to infinite mass energy, which is not physically attainable. The speed limit is enforced by how energy, mass, and space-time interact. E equals mc² enters here as the baseline. Even at rest, an object has energy. That rest energy contributes to its inertia. Motion adds energy on top of that, increasing the object's resistance to acceleration. Time dilation and length contraction are not add-ons. They are the space-time expressions of this energy accounting. General relativity extends this picture further. It incorporates gravity by allowing space-time itself to curve in response to mass energy. Time no longer just dilates due to motion. It also dilates due to gravity. Clocks closer to massive objects tick more slowly than clocks farther away. This effect has been measured with extraordinary precision. Even small differences in altitude produce measurable differences in time. Once again, E equals mc² is part of the explanation. Gravity responds to energy, not just to mass. A massive object curves space-time because its mass represents an enormous concentration of energy. That curvature affects how time passes nearby. This means that time is not a universal flow. It is local. It depends on where you are and how you move. There is no single cosmic clock ticking uniformly everywhere. There are only local clocks, each following its own path through space-time. This idea often feels unsettling because it challenges the notion of a shared present. If time flows differently for different observers, then the idea of a universal now becomes difficult to define. Events that are simultaneous for one observer may not be for another. This does not mean reality is inconsistent. It means simultaneity is relative. The deeper message here is not that time is an illusion. It is that time is flexible. It is part of the structure of space-time, shaped by energy and motion. E equals mc² ensures that mass energy contributes to that shaping even when it appears still. Space too loses its absolute status. Distances depend on how space-time is sliced by observers. Geometry becomes dynamic. The universe is no longer a static container. It is an active participant. This redefinition has profound implications for how the universe is understood. It explains why gravity affects light. It explains why time slows near massive objects. It explains why energy contributes to gravity even when it is not tied up in matter. It also explains why classical intuitions work so well most of the time. At low speeds and weak gravitational fields, space-time behaves approximately like the rigid stage people once imagined. Time flows almost uniformly. Space appears flat. Classical physics emerges as a highly accurate approximation. Relativity does not discard this approximation. It situates it. It tells you when it applies and when it needs refinement. The equation E equals mc² plays a similar role. It does not invalidate classical energy concepts. It extends them. One of the most subtle consequences of this framework is how it reshapes causality. Because the speed of light is a maximum speed for information, space-time is structured into regions of influence. Events can only affect other events within certain boundaries. These boundaries are determined by light cones, geometric structures that define what can influence what. Energy, mass, and space-time together enforce these causal limits. You cannot send a signal faster than light. You cannot affect events outside your future light cone. This consistency is not imposed externally. It arises naturally from the geometry of space-time and the behavior of mass energy. This means that the universe is not just governed by rules. It is structured in a way that makes certain things impossible. Those impossibilities are not arbitrary. They're consequences of deeper relationships. E=mc² is part of that network. It ensures that mass energy behaves in a way that is compatible with space-time geometry. It keeps the universe coherent. The deeper message of relativity is not simply that time slows down or space contracts. It is that the universe does not privilege a single perspective. Physical laws look the same to all observers, even if their measurements differ. This principle of relativity is upheld by the interplay between space-time structure and mass energy. The equation reinforces this by ensuring that energy and mass transform correctly between observers. What one observer measures as energy, another may measure differently, but the underlying relationships remain consistent. The total mass energy of a closed system is conserved in a relativistic sense. This consistency is what allows physics to make universal statements despite relative measurements. It is what allows predictions to hold across frames of reference. It is what makes the universe intelligible rather than chaotic. Time, then, is not a background river carrying everything along. It is a dimension intertwined with space, responsive to energy and motion. E=mc² ensures that even the energy bound into matter contributes to how that dimension behaves. This does not strip time of meaning. It enriches it. It explains why time feels steady under ordinary conditions and strange under extreme ones. It explains why GPS satellites need relativistic corrections to function accurately. It explains why experiments with fast-moving particles confirm time dilation. As you sit with these ideas, it is not necessary to visualize warped grids or bending space-time. Those images are helpful but optional. What matters is the shift in perspective. Time and space are not separate containers. They're dynamic aspects of reality shaped by what exists. The equation is one of the keys that makes this picture consistent. Without it, energy and mass would not fit cleanly into the geometry of space-time. With it, everything aligns. Mass, energy, space, and time are not separate pieces assembled afterward. They're aspects of a single structure, responding to one another according to consistent rules. For a long time, reality felt comfortably divided. There was the physical world made of solid objects, and there were the forces that acted upon them. There was matter, and there was motion. There was substance, and there was activity. Science described how these pieces interacted, but it rarely questioned whether the pieces themselves belonged to separate categories. The world felt like a collection of things connected by rules. What E=mc² did, slowly and almost quietly, was dissolve one of the most fundamental boundaries in that picture. It suggested that what we call things and what we call actions are not as different as they appear. And once that suggestion was taken seriously, it changed not just physics, but how reality itself was understood. Before this equation, mass was thought of as a passive property. It described how much matter something contained and how strongly it resisted being moved. Energy, by contrast, was dynamic. It flowed, transformed, and powered change. These roles felt natural. Objects stayed. Energy moved. The distinction was reinforced by daily experience. A rock sits still. Heat spreads, light travels. Motion happens to matter, not as matter. E=mc² undermined that narrative without announcing itself loudly. It did not say that rocks suddenly behave like light or that energy becomes tangible in ordinary life. It said something more subtle. It said that mass itself is a form of energy, not metaphorically, not philosophically, literally. And that claim required a rethinking of what it means for something to exist. Once mass was understood as energy in a stable configuration, the idea of substance began to shift. Matter was no longer the ultimate building block. It was an expression of something deeper. The solidity of objects was not the absence of energy, but the result of energy arranged in a way that resists change. This single insight collapsed a conceptual wall that had stood for centuries. Reality was no longer neatly divided into what is and what happens. Being and doing blurred together. Existence itself became a dynamic state rather than a static one. Objects did not merely occupy space, they embodied energy. Their persistence was not a given, it was an outcome. This change in perspective had ripple effects. It altered how physicists thought about forces, interactions, and even identity. If mass is energy, then inertia, gravity, and resistance to motion are not mysterious properties attached to matter. They are consequences of energy content. The question shifted from, what is this thing made of, to, how is energy organized here? This reorganization of thought extended beyond equations and experiments. It affected how explanations were framed. Classical physics often explained behavior by appealing to forces acting on objects. Relativity reframed behavior in terms of geometry and energy distribution. Objects did not move because they were pushed. They moved because space-time told them how to move, and space-time itself was shaped by energy. E=mc² was essential to this shift, because it ensured that mass contributed fully to space-time curvature. Without it, matter would curve space in one way and energy in another. Reality would fracture into competing descriptions. The equation unified them. This unification made the universe feel less like a machine made of separate parts, and more like a coherent system governed by deep relationships. It suggested that the same principles apply at all scales, from particles to galaxies. The universe became less compartmentalized and more holistic. One of the most profound changes this brought about was in how permanence was understood. Matter had once been seen as the stable foundation beneath fleeting processes. Energy came and went, but matter endured. E=mc² revealed that endurance itself was a kind of energy balance. Nothing was fundamentally permanent. Stability was a condition, not an essence. This did not make reality feel fragile, it made it intelligible. It explained why things last as long as they do. It explained why change requires effort. It explained why the universe is both dynamic and reliable. The equation also reshaped how beginnings and endings were interpreted. Creation no longer meant bringing substance into existence from nothing. It meant rearranging energy into new configurations. Destruction no longer meant annihilation, it meant dispersal. These were not semantic tricks. They were reflections of how the universe actually behaves. This shift affected cosmology profoundly. The early universe was no longer imagined as a sudden appearance of matter, but as a transformation of energy under extreme conditions. The future of the universe became a question of how energy continues to spread and reorganize. Reality became a story of transitions rather than events. Even the idea of emptiness changed. Empty space was no longer truly empty. It carried energy. It participated in the universe's dynamics. The distinction between something and nothing became less sharp. Reality became richer, more layered. On a more personal level, this change altered how humans understood their place in the universe. If matter is energy, then the boundary between living beings and the rest of the cosmos softened. Bodies are not exceptions. They are particular arrangements of energy following the same rules as everything else. This does not reduce life to physics. It situates life within a broader continuity. E=mc² also challenged the intuition that understanding makes the world less meaningful. Some feared that reducing matter to energy would strip reality of substance. The opposite happened. Reality gained depth. Objects were no longer just there. They carried histories of energy transformations reaching back to the earliest moments of the universe. This perspective made the universe feel less like a collection of inert things and more like an ongoing process. Not a chaotic one, but a structured one. Patterns persisted because energy arranged itself in ways that allowed persistence. Change occurred because energy flowed. Importantly, this did not turn reality into abstraction. It grounded abstraction in measurement. The equation did not invite speculation without constraint. It demanded precision. Every claim could be tested. Every transformation could be accounted for. Reality became more unified without becoming vague. The equation also forced humility. It revealed that categories humans had relied on were conveniences, not truths. Mass and energy were not separate because the universe demanded it. They were separate because human experience made it useful to treat them that way. E=mc² reminded science that intuition must sometimes yield to deeper consistency. This humility extended to time and space as well. Once mass energy was recognized as shaping space-time, the idea of an objective, universal backdrop dissolved. Reality was no longer something that happened in time and space. Time and space were part of what happened. This reframing had consequences for how causality was understood. Causes and effects were no longer just sequences in time. They were relationships constrained by geometry and energy. The universe enforced limits not through rules imposed from outside, but through its own structure. E=mc² played a role here by ensuring that energy content determined how those limits manifested. It connected what exists to what is possible. Reality became less arbitrary and more coherent. Another subtle shift occurred in how explanation itself was valued. Classical explanations often aimed to reduce phenomena to simpler components. Relativity, supported by this equation, emphasized relationships instead. Understanding came from seeing how pieces fit together, not from isolating them completely. This relational view changed how reality was described at every level. Particles were not just objects with properties, they were excitations of fields. Fields carried energy. Energy shaped space-time. Everything was connected. The equation also blurred the line between matter and radiation. Light was no longer just something that illuminated matter. It carried momentum. It exerted pressure. It contributed to gravity. Matter was no longer just something light interacted with. It was energy like light, but configured differently. This symmetry was profound. It suggested that the universe was built from fewer fundamental ingredients than previously thought. Complexity arose from arrangement, not from an ever-growing list of basic substances. As this understanding settled in, reality became less about categories and more about patterns. What mattered was not whether something was matter or energy, but how energy was distributed and constrained. The universe became a tapestry of configurations rather than a warehouse of objects. This did not make science colder or more mechanical. It made it more economical. Explanations grew leaner but deeper. Fewer assumptions were needed. More phenomena fell under the same principles. E=mc² became iconic not because it was clever, but because it captured this shift succinctly. It was not just a formula, it was a statement about unity, about the refusal of the universe to be neatly divided into static and dynamic, substance and action. That is why the equation changed how reality was seen. It did not add a new piece to the puzzle. It showed that the puzzle pieces people thought they had were cut from the same material. Once that realization took hold, there was no going back. Physics moved forward with a new sensibility, one that valued relationships over categories, one that saw stability as an achievement rather than a default, one that understood existence itself as an energetic condition. E=mc² did more than explain energy release or stellar light. It quietly rewired how reality itself was understood. It replaced a world of separate things with a world of connected processes, and that change continues to shape how the universe is studied, described, and quietly contemplated, moment by moment, without ever needing to announce itself again. At some point after equations have been written, tested, confirmed, and woven into the structure of modern physics, a quieter question begins to surface. It is not a question about numbers or predictions. It is not about whether an equation works. It is about what it changes in the way the world is understood. E=mc² reaches that point very naturally. Once you accept that it is correct, once you accept that mass and energy are deeply connected and interchangeable under the right conditions, the mathematics recedes slightly into the background. What remains is a shift in perspective that mathematics alone does not fully describe. This shift is not mystical. It does not require symbolism or metaphor to exist. It arises simply from taking the equation seriously and following it all the way through everyday assumptions. For centuries, people lived with an intuitive picture of reality that felt solid and reliable. Things were made of matter. Matter had weight. It occupied space. Energy was something separate, something that moved through matter, powered machines, and eventually faded away. That picture did not feel like a belief system. It felt like common sense. E=mc² did not attack that picture directly. It did not say common sense was foolish. It said common sense was incomplete, and once that incompleteness is acknowledged, it becomes difficult to look at the world in quite the same way again. One of the most subtle changes this equation introduces is in how solidity is interpreted. Solidity feels like permanence. A table feels solid because it resists your hand. A wall feels solid because it stops your movement. These experiences reinforce the idea that matter is something fixed and unchanging. Yet physics now tells us that solidity is not a fundamental property. It is an emergent one. It arises from energetic interactions at microscopic scales, interactions that are stable enough to feel immovable at human scales. When mass is understood as stored energy, solidity becomes a behavior rather than an essence. Objects are not solid because they are made of a different kind of substance than energy. They are solid because energy is arranged in patterns that resist change. This is not a poetic idea. It is a practical one. It explains why objects behave consistently without appealing to hidden substances or special categories. This perspective also changes how fragility and strength are understood. A fragile object is not fragile because it lacks energy. It may contain just as much mass energy as a stronger object. It is fragile because the way that energy is arranged allows it to be rearranged easily. Strength and weakness become questions of structure rather than substance. Another quiet shift appears in how motion is perceived. Motion used to feel like something imposed on matter. You push an object and it moves. Energy enters the system and behavior changes. In the relativistic picture, motion is not just an add-on. It is deeply tied to energy content. As energy increases, inertia increases. Motion changes how mass energy participates in space-time. This leads to a more relational understanding of reality. Objects are no longer defined solely by what they are, but by how they relate to energy, motion, and space-time. Identity becomes contextual. A particle at rest is not the same physical entity as the same particle in motion at high speed, even though it remains the same particle. Its energy content is different, its behavior is different, its relationship to time is different. This does not mean reality is unstable or subjective, it means reality is structured. Properties emerge from relationships rather than existing in isolation. E=mc² is one of the rules that govern those relationships. Meaning beyond mathematics also appears in how limits are understood. The speed of light is not just a number, it is a boundary. It defines what is possible. It defines how quickly cause and effect can propagate. E=mc² incorporates that boundary into the very definition of mass energy. This tells you something important about the universe. It is not infinitely flexible. It has constraints built into its fabric. Constraints often feel restrictive, but in physics, they are enabling. The fact that mass energy is conserved makes prediction possible. The fact that the speed of light is finite makes causality meaningful. The fact that energy can be stored as mass makes stability possible. Without these constraints, the universe would be chaotic and unintelligible. Seen this way, E=mc² is not just a conversion formula, it is a statement about balance. It says that the universe trades one form of existence for another without loss. It says that change is allowed, but disappearance is not. It says that stability is not accidental, but earned through energetic arrangement. This has implications for how time is felt. If mass is energy, and energy influences time, then time itself is not a neutral backdrop. It responds to what exists. Clocks tick differently depending on energy density and motion. This does not make time unreal. It makes it responsive. Responsiveness replaces absoluteness. Space responds to energy. Time responds to energy. Matter responds to energy. Nothing stands entirely apart. This interconnectedness does not blur everything into sameness. It preserves distinctions while showing how those distinctions arise. One of the most meaningful consequences of this view is how it reframes the idea of change. Change is no longer something that happens to an otherwise static world. The world itself is a process. Structures persist because energy configurations persist. When configurations shift, structures change. This applies equally to stars, atoms, and everyday objects. E = mc² supports this process-based view by removing the illusion of fundamentally static substance. There is no unchanging core beneath change. There are only arrangements that last longer or shorter periods of time. This can feel unsettling if permanence is equated with meaning. But physics does not suggest that meaning requires immutability. It suggests that meaning arises from patterns that endure long enough to matter. Stability is not eternal, it is sufficient. Another quiet implication appears in how scale is understood. The same equation applies at all scales. It governs nuclear reactions and stellar processes. It governs the mass of everyday objects. It governs the energy content of the universe as a whole. This universality suggests that reality does not change its rules as it grows larger or smaller. It uses the same ones everywhere. That consistency carries a certain kind of meaning. It tells you that understanding gained in one context can apply in another. It tells you that the universe is not stitched together from unrelated regions. It is coherent. This coherence does not make the universe simple. It makes it navigable. Complexity arises from repeated application of simple rules under different conditions. E = mc² is one of those rules. Meaning also appears in what the equation does not do. It does not explain why the universe exists. It does not explain why the constants have the values they do. It does not explain why there is something rather than nothing. Those questions remain open. But the equation does show that whatever exists behaves consistently. That consistency is not trivial. It is the foundation on which deeper questions can even be asked. There is also a human dimension to this shift that is easy to overlook. When matter is understood as energy, the sharp boundary between humans and the rest of the universe softens. Bodies are not made of a special substance exempt from physical law. They are energy configurations like everything else. This does not reduce human experience to physics. It places physics as one layer of description among others. Emotions, thoughts, and experiences are not explained away by E = mc², but they occur in a universe where mass-energy relationships shape time, motion, and structure. The equation provides context without replacing other kinds of meaning. In that sense, meaning beyond mathematics is not about extracting philosophy from equations. It is about recognizing what equations quietly change in the background of thought. Once mass is no longer treated as inert substance, the world becomes less about things and more about relationships. Less about static categories and more about processes. This shift aligns with developments across science. Biology emphasizes systems rather than isolated organs. Ecology emphasizes networks rather than individual species. Neuroscience emphasizes patterns rather than single neurons. Physics, through equations like E = mc², participates in the same movement. The universe appears less like a collection of separate objects, and more like a layered process unfolding over time. E = mc² supports that view by ensuring that matter itself participates in energetic flow, even when it appears still. Importantly, this does not demand constant attention. You do not need to think about mass-energy equivalence while drinking a glass of water or walking through a room. The world behaves the same whether you reflect on it or not. Meaning here is not about changing experience, It is about deepening understanding. That deepening does not lead to a final conclusion. It opens further questions. If mass is energy, where do these energy patterns come from? If space-time responds to energy, why does it have the properties it does? If the universe is coherent, why is it structured in this particular way? E=mc² does not answer these questions. It makes them sharper. It removes misleading assumptions so that questions can be asked more clearly. The equation's greatest impact may not be what it calculates, but what it dissolves. It dissolves the idea that matter and energy are fundamentally different kinds of things. It dissolves the idea that solidity implies emptiness of activity. It dissolves the idea that stability requires permanence. What remains is a universe that is consistent, structured, and deeply interconnected. A universe where meaning does not come from rigid categories, but from relationships that endure long enough to shape experience. As everything you have heard so far settles into the background, it may begin to feel as though the equation itself is no longer at the centre of attention, not because it has been forgotten, but because it has quietly done its work. E=mc² does not need to be repeated again to remain present. It has already shaped how the pieces fit together. What remains now is not a problem to solve or a conclusion to reach, but a way of sitting inside the picture that has slowly taken form. At this point, it can be helpful to notice your own surroundings again. The room has likely not changed. The objects around you are still where they were. The air still feels the same, and yet the explanation layered beneath those ordinary details may feel slightly different than it did before. Not heavier, not more intense, just deeper. The familiar world remains familiar, but it no longer feels empty of explanation beneath its surface. The idea that the universe is filled with energy does not mean that everything is active all the time. It means that activity and stillness are not opposites. They are different expressions of the same underlying reality. When something appears still, it is not lacking energy. It is balanced. When something changes, that balance shifts. The equation does not turn the universe into constant motion. It explains why rest is even possible. This can be a surprisingly grounding thought. Much of daily life is spent responding to movement, change, urgency. Messages arrive. Tasks demand attention. Time feels like something that runs out. Against that backdrop, the idea that mass itself is energy held in place offers a different rhythm. It suggests that persistence is not passive. It is active equilibrium. Things last because they are energetically allowed to last. Your own body fits into this picture without effort. It does not need to be elevated or diminished by physics to belong. It is a stable arrangement of energy that breathes, adjusts, repairs itself, and maintains balance moment by moment. Nothing about this understanding interferes with how it feels to rest. If anything, it explains why rest works, why stillness can be restorative rather than empty. Even time, which so often feels like pressure, softens slightly when viewed through this lens. Time is not a universal current sweeping everything forward at the same rate. It responds to energy and motion. It stretches and compresses. It adapts. The time you experience right now is local. It belongs to this moment, this position, this state of rest. There is no requirement for it to match any other clock. That idea alone can be enough to let urgency loosen its grip. If time is not absolute, then there is no single pace you are failing to keep up with. There is only the pace appropriate to where you are and how you are moving. Rest is not falling behind. It is a different trajectory through space-time. The universe itself does not rush. Stars burn steadily for millions or billions of years. Galaxies drift, collide, and reshape over timescales that dwarf human history. Even dramatic events, when viewed cosmically, are part of longer, slower arcs. E=mc² is embedded in all of this, not as a source of drama, but as a regulator. It ensures that change unfolds within limits. Those limits are what make the universe habitable. They allow light to travel without tearing matter apart. They allow energy to be released without dissolving structure instantly. They allow mass to exist as something you can lean against, sit on, or lie down upon. The equation does not make reality volatile. It explains why it is dependable. It can be tempting to think of physics as something that strips the world of comfort, replacing familiarity with abstraction. But the deeper truth is often the opposite. Understanding how stable the universe has to be in order to look ordinary can increase appreciation for that ordinariness. The fact that objects remain objects is not trivial. It is earned through balance. Nothing around you is fragile by default. It may break under the right conditions, but it is not on the verge of collapse. The energy bound into matter is not trying to escape. It is content to remain as it is unless acted upon in very specific ways. This quietness is part of the universe's character. Resting inside a universe of energy does not mean being surrounded by motion. It means being supported by structure. It means that even when you stop moving, even when you close your eyes, the systems that hold you in place continue without effort on your part. Gravity remains consistent. Time continues locally. Matter retains its form. The equation you've been exploring does not ask you to feel awe or fear. It does not ask you to imagine extremes. It simply offers a description of how deeply connected things are. That connection does not demand attention. It functions whether you think about it or not. When people first learn that mass is energy, they sometimes feel unsettled, as though solidity has been undermined. But solidity has not been taken away. It has been explained. The table does not become less solid because it is energy. It becomes more intelligible. Its resistance, its weight, its persistence all follow from that fact. The same is true for the larger universe. Knowing that stars shine because mass becomes energy does not make starlight feel harsh or dangerous. It explains why it arrives gently enough to warm skin rather than burn it instantly. It explains why the sun can rise day after day without dramatic fluctuation. The universe is not balanced on a knife edge. It has margins. It has tolerances. It has room for complexity because its fundamental relationships are stable. E equals mc² is one of the expressions of that stability. Even the future, which often feels uncertain, is constrained by these same principles. Whatever unfolds will do so within the same accounting system. Energy will not vanish. Mass will not appear without cause. Structures may change, but balance will remain. This does not mean everything is predictable. Complexity arises precisely because simple rules can produce rich outcomes. But unpredictability is not chaos. It is bounded. It operates within a framework that does not allow anything at all to happen. That framework is quiet. It does not announce itself. Most of the time, it stays far beneath awareness. You do not feel mass-energy equivalence when you breathe. You do not notice space-time curvature when you lie down. The world feels simple because it is allowed to feel simple at human scales. As you rest now, there is nothing you need to hold in mind. The explanation does not need to be rehearsed. The equation does not need to be visualized. Understanding does not require effort in this moment. It can remain diffuse, like background knowledge that does not intrude. The universe does not require your attention to function. It has been unfolding for billions of years without waiting for acknowledgement. You're not responsible for keeping it coherent. The same relationships that hold stars together also hold the floor beneath you and the air around you. In that sense, resting is not a withdrawal from reality. It is participation in one of its most common states: stability, balance, persistence. These are not pauses between events. They are outcomes in their own right. The idea that everything is energy does not make rest feel artificial. It makes it natural. Energy does not have to move to exist. It can remain arranged, constrained, held in patterns that last. Your own stillness fits into that description without contradiction. Nothing in this understanding demands a final thought or a closing insight. The universe does not resolve itself. It continues. The explanation does not end. It simply fades into the background where it belongs. If your attention drifts now, that is appropriate. If thoughts slow, that is consistent with the picture you have been building. There is no need to arrive anywhere else. The framework is already in place, quietly supporting whatever comes next. E equals mc² does not need to be remembered explicitly. Its implications remain whether or not the symbols are recalled. Matter will continue to behave as stored energy. Energy will continue to shape space and time. The universe will continue to balance change and stability without interruption. As you rest, you are not stepping outside that system. You are resting within it, supported by relationships that do not require effort, explanation, or attention in this moment. The same rules apply, gently, continuously, without asking anything from you at all.